talk more about memory interference and quality of service. We'll still be focused on the memory system, as you can see. That focus will not go away. But we're going to look at different topics. There's another topic that's fascinated many people, and a lot of the ideas that I'm going to describe are making their way into the systems we design today. Basically, what we're going to talk about is shared resource design for multi-core systems. We're going to start with memory controllers especially, but let me motivate the problem first. Is this too loud? I feel I hear an echo. Better? Okay. Okay, so remember this picture? This picture is all about memory. And if you look inside it, most of the system is really dedicated to storing and moving data. And we covered a lot of that system so far. But we didn't cover it as a shared resource as much. So if you look at this memory system, the caches, interconnects, memory controllers, memory, storage, interconnects, they're all shared between different hardware contexts that are running different threads inside these cores. In fact, there's very little that's private to a hardware context that's running inside a core. Most of the system is really shared. And that sharing leads to issues. I mean, that sharing is good. Basically, the concept is really resource sharing. It's a very fundamental concept. It doesn't exist just in computers, right? It exists in human life. You share resources. Instead of dedicating a particular resource, in this case hardware resource, to a hardware context, you allow multiple contexts to share it. And there are many example resources. You could share functional units in a multi-thread engine. You could share the pipeline if you have multiple hardware contexts running on the pipeline with simultaneous multi-threading, for example. You could share the caches. You could share the buses. You could share the memory, interconnect, storage. And these hardware contexts can be running different threads belonging to the same application or different applications. We're going to look at different applications and the issues that arise because of that a lot, but we're also going to talk about the same application, different threads from the same application sharing these resources. So why would you like to do this? Why would you like to share resources? Hopefully the answer is obvious, because you would like to improve utilization and efficiency, or throughput, right? Meaning that resources are not always required by all threads all the time. Sometimes some threads leave the resource idle, and when you leave it idle, some other thread can now use it. As a result, this improves utilization, this improves cost efficiency, because you don't need to replicate the resource, and once you replicate the resource may become idle. And also there is no need to replicate shared data. If you have multiple threads sharing data for whatever reason, because they're programmed that way, if you actually share the caches between those threads, that shared data doesn't get replicated. It just stays at one location. Right? So that's good. That helps. That's also another utilization concept that improves your utilization or efficiency. Right? It reduces communication latency, because if you have a shared resource, now you can communicate through that shared resource between different threads. For example, if the shared data, again, between two different threads is kept in the same cache in a simultaneous multi-threaded processor. Right? If the threads are running together in the same pipeline, they share the L1 cache, they can access that shared data. If the threads are running together and they have their own caches, now they need to actually replicate that data, right? And if one writes to that data, then the other needs to be aware of that write, which means that you have some communication latency. So resource sharing is good for reducing communication latency. And this is also compatible with the shared memory model, because what we've been talking about is shared memory model, right? You have a single view of memory by different threads of the same application, and they can basically address a location, and they can share data within that location. And if you have the physical resource also shared across those threads, then it's compatible. Okay, so these are the big advantages of resource sharing. And you can apply this to human life also, right? By sharing resources, you can actually do better utilization, cost efficiency, as opposed to everyone having their own car, for example. You have buses or trams that are much more efficient and much better utilized. Because if everybody has their own car, it may not be very well utilized, right? That's an obvious example of a shared resource. Okay. But of course, there are disadvantages to shared resources. Just like in human life, you have contention for shared resources. When the resource is not idle, And when some other thread wants to use it, that thread cannot use it at this point. This is true for time and space. So you may have idleness in time, you may have idleness in space. If, for example, a cache space, a particular location in the cache is occupied by one thread, another thread needs to reoccupy it. It cannot use it directly. It needs to basically kick out something belonging to some other thread. Which means that this contention leads to performance loss for each of the threads or for some of the threads, right? It could be all of the threads, actually. For example, if you're having a bank conflict between two threads, and the two threads have an access pattern such that they're all causing row buffer conflicts to each other, then both of the threads' performance degrades compared to when each thread is run alone, right? When you're running alone, you would get nice row buffer hits, let's say, but when you're running interleaved with some other thread, together with some other thread, both of them may be getting row buffer conflicts. As a result, overall system performance can actually degrade. So there are cases where this happens. And basically, thread performance can be worse than when it's run alone. And all of the system's performance can be worse than when you compare this to executing threads one by one. It doesn't happen often, but it could happen. So also, resource sharing eliminates performance isolation, meaning that because you don't have a dedicated resource for each hardware context, these contexts have different performance when they run together with different applications. You get inconsistent performance across runs. And we will see examples of this. If you isolate the resources, you have your own resources, and you can predict your performance potentially, right? Your performance is isolated, it's not affected by somebody else. If you have resource contention, your performance is affected by somebody else, right? For example, if you go to Tannenbar to get coffee, if everybody had their own door, you would get perfect performance isolation and your own servers, right? But because that door is shared and it's a huge bandwidth bottleneck, that's a great example of a bandwidth bottleneck, actually, the Tannenbar door. Especially go there when, if you're unlucky to go there when 100 people are going inside and you're behind those 100 people, good luck. That door will lead to a huge performance, not only reduce your performance, but also eliminate your performance isolation. When you go there alone, you will get performance that's great, but when you go there behind 100 people, you'll get terrible performance. So your performance is not isolated. Okay, so basically thread performance depends on co-executing threads, and if you have uncontrolled sharing, if you don't control this sharing somehow, your quality of service, the quality of service you get degrades. And this is a problem in real life, as we just discussed. This is a problem in hardware also. This uncontrolled sharing causes unfairness and starvation, which may not be good. So we want resource sharing, actually. Resource sharing is nice because of the reasons that we discussed. You get efficient utilization. But we need to find a way of efficiently and fairly utilize these shared resources while avoiding as much as possible these three things. Okay, so let me give you an example. This is an example with shared caches. This is from a relatively early paper that looks at fair cache sharing in 2004 or so. So let's say you have this particular thread. When it's run alone, it needs this much cache. And you have this other thread. When it's run alone, it needs this much cache. But when they're run together, this particular thread doesn't get as much cache, and this one hogs the cache. As a result, the throughput of this particular thread may be reduced because of this unfair cache sharing, because they're sharing the resource. So for example, actually this thread may be a streaming thread. It's streaming through memory. It doesn't have a lot of good reuse in the cache, but it keeps allocating cache blocks. And this thread may be a thread with a small working set, but this small working set doesn't remain in the cache because this thread keeps kicking it out. As a result, this thread's performance degrades significantly. This thread's performance doesn't benefit much from caching, and you have a not so good not so good sharing of the resources because nobody makes use of the cache in that case. So this happens, and people have developed mechanisms to partition the shared caches, which we may go into later on. Of course, if you partition the cache, performance becomes more isolated, but if you partition the cache, then you have potentially some other problems. Meaning if this core needs more cache than the partition that it's given to, it cannot use it. So partitioning also has downsides. Okay, So I'll motivate the need for quality of service a little bit also. Basically, why is unpredictable performance or lack of quality of service bad? I'll go through this relatively quickly. Hopefully some of this is obvious. But this makes programmers' life difficult if, let's assume that your performance is not isolated. Your performance is very much dependent on other threads that are running on in the system. You may optimize your program as much as you want. It doesn't matter maybe, right? Because your performance optimizations, let's say you optimize your robot for locality really nicely, but your performance is very much dependent on some other threads, robot for locality and access patterns. Clearly, as a programmer, you cannot optimize any other thread that you're running with, because these are completely different applications. As a result, your performance optimizations may not matter. So this actually makes, if you don't have performance isolation, it's not really good for program optimization or compiler optimization either. It causes, of course, there's a user level impact. If you care about a particular program, that program starves, then you actually don't like it, right? I always have this problem with my phone, for example. Whenever I need to get a response, I don't get the response sometimes, right? And that is essentially, that is usually because of some software shared resources. Actually, what is this? Microsoft Office. It used to have a shared software infrastructure between Word and Excel. This was a long time ago. And whenever you wanted to open a file or write to some big file, let's say in one of the programs, the other program got stalled because these were actually using the same shared software infrastructure to go to it was hard disk at the time, basically, to access the hard disk. Now that was a bad idea. Clearly they eliminated this right now, but that's an example of resource sharing. You have two different programs, you go through the same software infrastructure. When one is writing to the disk, the other cannot access the disk for whatever reason. That's a problem. That problem happens in hardware also. We're going to look more into hardware, but the resource sharing concept is much broader than hardware. It's also software. Okay, so if you don't have quality of service and good shared resource management, this also makes system management more difficult. So, for example, if you're running a data center and you want to maximize your efficiency when you're running the data center, and you put together multiple different virtual machines or applications, and you want to guarantee service level agreements for all of those virtual machines or applications that you have. But if your hardware resource sharing is not controllable, if hardware is not really satisfying some particular performance guarantee that you want, then you have a problem, because you promise some service level agreement to people who send you jobs, and the hardware itself is unfairly prioritizing some other job, right? So if this happens, then you cannot guarantee service level agreements, and as a result, maybe you don't put together multiple different applications with stringent service level agreement requirements. As a result, you have these multi-core systems that are underutilized completely in the data centers. In fact, a lot of data centers do this today. They basically, if some particular programs have high, stringent service level agreement requirements, they actually put those programs into their own servers and don't schedule them together with other programs that may or may not have service level agreement requirements. As a result, what you have is a lot of inefficiency in the data center because you're really dedicating servers to particular programs. But if you actually had hardware design or system design overall that provides service level agreement guarantees, if you could actually push these into the system and the system basically satisfies some of these guarantees as opposed to being unfair or uncontrolled, then you could actually increase your efficiency significantly as well. So basically, the lack of quality of service or unpredictable performance leads to a lot of issues across the stack. And I think a lot of these are really important, and they affect a lot of things. I think this is actually really not so good, because you learn a lot about optimizing your programs, right, in compilers and whenever you write programs, but some other program that is scheduled next to yours destroys your performance, and it doesn't matter whatever you do as a programmer. That should not happen, I think. Okay, so let's talk about resource sharing and partitioning a little bit. I briefly talked about this, but basically these are two ends of the spectrum, and we're going to have them meet in the middle during the course of these lectures. Sharing clearly improves throughput. You have resource sharing, you get better utilization of space, better utilization of time. meaning bandwidth. And we discussed this already. But if you partition the resources, that's good for performance isolation, right? That's how you get predictable performance. If a thread has a dedicated cache, dedicated memory controller, dedicated buses, dedicated main memory, dedicated SSD, then you know what performance you're getting because its performance is not affected by anything else. Now that's the downside of this is of course very high cost, right? And also if you dedicate some resource, then if you need more resource than that dedicated, you may not be able to use, well, you don't use somebody else's resource that may be going idle, right? If this thread needs, for example, if you give everyone 64 megabyte cache space, and if a particular thread needs more than 64 megabytes, let's say 128 megabytes, let's say 127 megabytes, and if another thread needs only 1 megabyte, you cannot share the resources, even though the total resource is 128 megabytes, right? One thread's performance degrades a lot because it gets only 64 megabytes, even though it needs 127. Another thread doesn't make use of the 64 megabytes it's given because it needs only 1 megabyte, right? So that's the downside of partitioning. You get both high cost as well as not so good utilization. So the key question is, can we get the benefits of both? And that's what we're going to try to achieve as much as possible in these lectures. And the idea is you start with sharing the resources, but design them such that they're efficiently utilized, they're controllable and partitionable in some way. They satisfy some sort of fairness and quality of service requirements. And hopefully the goal is to have no wasted resource through sharing and some partitioning mechanisms, or in other words, quality of service mechanisms for different threads. Okay? So if you look at this is another picture that's similar to what I shown you over here, but basically memory system is the major shared resource today. There are shared resources between threads inside the cores. We're not going to touch those, at least in this course. But recall that there's a lot of sharing inside here also between different threads if you have simultaneous multi-threading. But we're going to look at some of these things, and we're going to focus a lot on the memory controller today especially. Okay, basically the issue is that different threads inject different requests to these shared resources, and their requests interfere with each other. Then what do you do when these requests interfere? And I've already shown you that. The problem is threads share the memory system, but memory system, at least if you design it without this sharing in mind, it doesn't distinguish between different threads' requests. At least this was the case, especially in 2006 or so. Things are changing right now, and I'll give you the changes, but if the memory system doesn't distinguish between different threads' requests, it's essentially free for all. The memory systems are shared based on demand, and your control algorithms are thread unaware because you don't distinguish between different threads' requests, and as a result, thread unfair. Meaning that aggressive threads can deny service to others, and we've seen this earlier. I'm going to go into more of that. And they do not try to reduce or control inter-thread interference, the existing memory systems. As a result, you get all kinds of performance isolation and quality of service problems. And you've seen this picture before. Basically, this is an experiment that we did in 2006 on real processors. It's an Intel processor, I think. It used to be Intel Pentium D at the time. Basically, if you run one application, MATLAB, an aggressive application, very streaming, doing matrix multiplication heavy on large matrices. If you run it together with GCC, both applications slow down because of resource sharing, but one slows down a lot more than the other one. So the GCC in this case slows down by 3x, MATLAB slows down by 7%. So clearly there's some unfairness going on, compared to when each of them is run alone. Of course, you measure the performance when MATLAB is run alone on the same system without any other application, and you measure the performance when MATLAB is running together with GCC. MATLAB slows down by only 7% when it's running with GCC, whereas GCC slows down by 3x when it's running with MATLAB. So not so good. Clearly this is one example of unfairness. Of course, unfairness, we'll talk about definition of fairness also, which is not easy to define as well. That's true for humans as well, right? In human life, fairness is not easy to define. How do you define it? But that's true for computers too. But we'll look into some definitions. Okay, so basically the problem in the previous case is you have unfairness in the memory controller. I'm going to go through this relatively quickly because you've seen this before, especially if you take digital technique. But basically, in this particular system, the shared resource was really the memory controller. Caches were not shared at the time. There were no shared caches. These are Intel's first multi-core systems. And we examined them and we basically looked at this problem. Essentially, you have a streaming application and a more or less random access application. When they run together, this is what happens. Memory controller gives priority to the streaming application. Doesn't sound very good. So we actually built these applications. One is called Stream, and this was based on an application called Stream, which really measures the memory bandwidth. So it's really a big memory bandwidth hog. And we made it an even bigger memory bandwidth hog by ensuring that all of the accesses are cache misses. So let's take a look at what this does. You basically copy one array to another array in a streaming manner. You can see that the index is streaming, but each access is a cache miss. So you have very sequential memory access in this one, very high roboffer locality, and it's very memory intensive. Now, if you to do the control experiment, we call this the memory performance hog. Actually, this actually hogs the performance of any other application that is run next to it, assuming you don't have a fair memory controller. We also wanted to look at a control application. This is a random access application. It basically does random memory access. You form the index to copy from array B to into array A in a random manner. Of course, you don't do this like this because you don't want this random number generation to be hogging the performance of your loop. So you actually pre-generate the indices, and then you can look at the paper as to how this is really done. But basically, this has random memory access, very low roboffer locality because of that randomness, but it's similarly memory intensive because you basically get cache misses because of those random accesses. Right? So if you run these two applications together, let's take a look at what happens. And if your memory controller is not designed to be aware of quality of service. We run this blue application as stream, red application is random, and the memory controller, let's say, gets first request, opens row 0, and schedules that request. And then the memory controller keeps getting some requests. It basically prioritizes the request that hit in the row buffer. And streaming application keeps accessing the same row over and over, whereas the random access application doesn't access the same row. But the streaming application essentially hogs the bank because the memory controller prioritizes accesses that hit in the row buffer, or requests that hit in the row buffer. And this can go on for a long time, depending on your memory controller and depending on the policies. Let's say you have a row size of 8 kilobytes and a cache block size of 64 bytes. You can service 128 requests of the streaming application before a single request of the random access application. Now that causes a memory hogging problem, as you can see. Right? And this is one reason for hogging memory. Basically, the memory controller is optimizing for row buffer locality, DRAM latency, and DRAM throughput, as opposed to different applications' quality of service. Right? So that's the problem. Well, why do they do it? You all know why they do it by now. A row conflict memory access takes significantly longer than a row hit access, and current controllers take advantage of the row buffer. And they use the FRF-CFS policy, which you know of. They prioritize row hits over other accesses, and all else being equal, they prioritize older accesses over other accesses. And this scheduling policy may not be bad for a single core system, although even in a single core system you have different streams. So you have the single core and then an I/O stream. If you're moving data from an I/O device into your memory, then you actually have, even in a single core system, you have this quality of service problem somewhat. But we'll talk about that later if we get to it. But this problem becomes much worse in a multi-core system because when multiple threads that are running on cores share the memory system, then maximizing DRAM throughput is not necessarily the right thing to do if applications have different requirements. Right? Basically, and we're going to talk about how to fix the problem, of course. So if we actually did this experiment, we ran the stream memory performance hog with the random access application, what I showed you, and you can read the results in the paper in more detail. But basically, you get results that look like this. Stream slows down little. Random slows down a lot, almost 3x. This is within 20%. This is almost 3x. Right? And you could run stream with some other application. It denies service to that other application. And at that time, Microsoft used to have these virtual machines. It was called virtual PC. I don't know if it exists anymore. Clearly, they didn't win the market in virtual machines at that time, after that time. But we wanted to look at the effect of this on virtual machines also. And some other application encapsulated in a virtual machine actually loses significant performance also. So basically, this is a problem. You can actually sneak this memory performance hog in, and then it denies service to whatever application you may really care about. Okay, and this becomes a bigger problem with more cores actually. This is simulation results where you have an application that's relatively streaming. This is a quantum computing simulator that has a lot of streaming access patterns. And some other application that you may actually care a lot about, like a video encoding, decoding system. And this application doesn't slow down a lot. This application slows down a lot. Because of this uncontrollable system, you have vulnerability to denial of service. You can maliciously write applications that slow down others, or you could inadvertently write applications that slow down others. That's a denial of service problem. It's just the intent that's difference, right? You become unable to enforce priorities or service level agreements because you run these 4 applications together. That's good. You basically try to make this make this one high priority. Let's say nothing changes because operating system actually has 4 applications to schedule on 4 cores, and they all get scheduled. Right? Priorities. The assumption in the operating system is that whenever you schedule something onto a core, it makes progress. And the implicit assumption is that if you actually have multiple cores, the cores make reasonably equal progress. It's not as rigorous, unfortunately, although there are some operating system schedules that are more rigorous today. It didn't used to be that way. But basically, the assumption is that cores actually make progress. But here, one core is making a lot more progress, if you will, from the memory system's perspective, whereas another core is making very little progress. So it's basically getting denied service. So if you don't support this fairness at the hardware layer, you cannot actually fix the problem easily at the software layer. You need to somehow identify the problem, that this is not making progress. So how do you identify that is another question. It actually becomes hairy to identify it. And once you identify it, what do you do is another question, right? You could actually deschedule this application and run only 3 applications together. But the same problem may appear when you run 3 applications together also, right? You're not guaranteed anything. So that's exactly why data center operators who have service level agreements on a program say, okay, we don't know how to do this. So if something has a stringent service level agreement requirement, we're going to run it alone. Meaning that you have 4 cores and you're wasting 3 other cores. And you're wasting corresponding power consumption, energy efficiency. You over-provision your entire data center in the end. Okay, so because of this. And you also get low system performance actually in this case because it turns out the applications that deny service to others tend to be very heavy in terms of memory intensity. They basically keep accessing memory a lot. As a result, they slow down other applications that do not access memory a lot. But implicitly, these applications are prioritized in the memory system, so they make very slow progress, but they were making very slow progress to begin with. But these applications, they actually have a lot of potential to make very fast progress. They have, once in a while, they send requests to memory. If that gets serviced, they can keep their cores busy for a really long time because they're not very memory intensive. But this application actually delays this not so intensive application for a really long time. As a result, you basically have low system performance because these cores are waiting for just a small number of memory requests that are being delayed from these because these cores are the requests from these cores are prioritized by the memory system. Whereas if you actually prioritize these workloads over here, the cores would make much faster progress, and this wouldn't be affected that much because this has, let's say, 100,000 requests, and this has a few requests across some time frame. Does that make sense? So yeah, the memory system is actually doing the wrong thing, even if it were optimizing for maximum performance. You don't want to prioritize the applications that are extremely heavy in terms of memory access because those are applications that are really slow anyway. If you delay them just a little, it may not matter that much. But if you delay these a lot, it matters a lot. And these are delayed a lot because the heavy applications are prioritized over the not so heavy applications. And we'll get back to this a lot, actually. It's a realization that took some time, but you don't want to prioritize memory intensive applications. But implicitly prioritizing for maximizing DRAM data throughput is implicitly prioritizing those applications, because these applications once in a while generate requests. They don't actually exercise the row buffer locality that you see. Okay, so as a result of this, you have an uncontrollable, unpredictable system, basically. Because your memory doesn't provide you some basics of fairness and quality of service, you cannot control it. You cannot predict what's happening. Performance isolation is another thing that we mentioned earlier. Okay, so this is an example of performance isolation, basically. So if you look at Omnet over here, it slows down by 8x. If you look at over here, it slows down by 4x. It depends on what the application is running with. And the slowdowns actually increase if you add more cores, and you can see that in the memory performance attacks paper that I mentioned earlier. Okay, so this becomes actually worse if you scale up the system. We're going to talk about interconnects later in the lectures. Well, that's going to be a lot of fun, I think. But if you look at a more scalable system, it looks like this. Meaning it has, in this case, this a bunch of cores, 64 cores. They're connected in some fashion with an interconnect. It's not stated here, but it's a mesh interconnect, two-dimensional mesh. And let's assume that you have a shared resource over here, a memory controller, and these cores want to access that memory controller to access memory. They basically need to somehow send their packets to the memory controller through the interconnection network such that they can access the memory controller, and the packets of each core travel this way. Those are the red lines. Which means that the shared resource is getting hogged by these 8 cores that are trying to access the same memory controller at the same time. You could actually orchestrate an attack like this, or this could happen naturally because of your memory mapping and these cores needing to access that memory controller. And once you have this, these links that are over here gets oversubscribed, so you get a lot of delays, and you get a lot of delay in the memory controller. As a result, you can get significant slowdown. So this paper shows that you could actually get very high latency increases because your network gets saturated, and we will talk about all of that network saturation when we talk about network. But this happens because you have a shared resource and you're not sharing it in a fair manner. Some applications are denying service to some others. Make sense? Okay, so that's one example from the paper. Basically, you have some attackers and you have some application that you're running in the other course. Okay, so this is the paper that we've been talking about. We may assign it, and this is the other paper that basically shows this and provides some solution in the on-chip network. But we'll talk about solutions in a little bit. Any questions so far? This is all good? Clear? Okay. Okay, so basically we have the problem of inter-thread. I'll call it inter-thread interference, but I use thread as a hardware context, but it's really also inter-application, inter-virtual machine, whatever granularity you want to increase it to, it's fine. It's basically 2 hardware contexts interfering with each other that has implications on the higher levels of the software stack. But basically they're interfering with each other in different shared resources, the memory controller, interconnect, and caches. And this interference is uncontrolled. How do we provide quality of service, or how do we solve the problem? We need to control it. There's no other solution, actually. I don't think so. Or you over-provision the system and don't share. And that's not a good solution, right? That leads to all sorts of energy and efficiency issues. Basically, we need to design interference-aware or quality of service-aware memory system. And there are 3 questions in designing this sort of systems, and questions or challenges. First of all, we would like to reduce the inter-thread interference as much as possible, if it's under our control. Meaning that if you actually reduce the inter-thread interference in an intelligent way, you can improve system performance and core utilization, and you can reduce request serialization and core starvation. And we're going to talk about some examples of this. Second, we want to have control over this inter-thread interference. You want to minimize it first, and then you want to control it, because you cannot completely eliminate it, right, if you're sharing resources. But you can at least have mechanisms to control it. We want to provide mechanisms so that we can enable the system software to enable quality of service policies. If one application requires some guarantee, that should be prioritized in the shared resources. That priority should be conveyed to the caches, to the memory controllers, to the interconnects, and those resources should respect that priority. As a result, you could enable now quality of service policies at the high level. Now the question is, what kind of things should be communicated? We'll talk about some of those things. For example, existing systems, this didn't used to be the case in 2006 or so, but existing systems provide mechanisms for the user to partition the caches across different applications. So you could say, this particular application gets 4 ways of the cache, this other application gets 2 ways of the cache, this other application gets 8 ways of the cache. That's cache partitioning. So that's one way of controlling the inter-thread interference. Existing systems, unfortunately, not yet. They do not provide, at least in the general purpose systems, they do not provide mechanisms to partition the memory bandwidth. That's not easy today, but people are working on it, and I think that's going to happen. In some other systems, this is such a big problem that those systems actually provide mechanisms, like the SoC memory controllers are actually much more advanced, because in the SoC you have so many different requirements. As a result, some of the ideas that we're going to discuss actually made their way into the SoCs much earlier than the general purpose systems. Because you really need quality of service when you have a hardware accelerator that needs to be satisfied and some other user level program that can be delayed potentially, right? Okay, so basically we need to have mechanisms to control inter-thread interference such that the software can provide quality of service policies. Of course, we want to provide high system performance when we do that, right? One policy could be what we have today. If the software wants to enforce quality of service policies, you have 1,000 cores, but you run the application only in 1 core and don't utilize anything else. That's a terrible solution. Okay, and the next one is a little bit more advanced maybe, but you really want to make the memory system more configurable or flexible because there are many goals that you need in different workloads. So sometimes you care about fairness, sometimes you don't care about fairness, right? Because the program is designed, and you're running a single program where multiple threads are interfering with each other, but the program is designed to provide fairness internally. I'm not suggesting that's easy to do, but that's possible. Sometimes you care about throughput, sometimes you don't care about it. Sometimes you care about latency, sometimes you care about bandwidth. So there are many different potential goals, and sometimes you care about performance guarantees, clearly. How do we actually have a flexible memory system that can switch between those different goals or satisfy different goals at the same time? This is a bit harder to achieve, of course, going forward, but this is also very important. That way, actually, you can be more efficient. We're going to look at examples of this, but we're not going to be able to solve the problem fully. But there's a lot more to do in this area, actually, in all of these areas over here. Okay, so there are 2 approaches that I'm going to talk about, 2 general approaches. One is, basically, if you want to enable answers to these questions, one approach is to make the resources smarter. And 3 example resources are memory controllers, interconnects, and caches. We want to design each of these shared resources to have a configurable interference control and reduction mechanism, quality of service mechanisms, basically. That's good. You put 3 different smart resources and hope that once you put them together, they all work nicely. Of course, that doesn't work very well because sometimes you need to coordinate between them. But this is a general approach. Make each resource aware of interference. The second approach, which is not necessarily which is orthogonal, but they can be combined together, which we will talk about later on, is dumb resources. Basically, keep the resources just like they are today, or maybe slightly modify them to be more efficient, but don't put quality of service mechanisms inside them. Keep them free for all, but do something else to provide quality of service in the system, or reduce or control interference. When I say provide quality of service, it's the same as reduce and control interference in a configurable way. And how do you do that? Well, you could do that by performing injection control or data mapping, right? So you can think of, let's see, which one? Can you record this? Is it good? Let me see. I need to understand the protocol here. Okay, that looks better. Oh, you need to go ahead. You can change the light while I'm doing this. So basically, how do you do this? There are multiple ways of doing it. One is, you can think of, these are your cores. Actually, Internet does this a lot, although Internet is a combination of both mechanisms. Okay, these are your shared resources. And cores are essentially clients that are injecting requests and getting responses from those shared resources. And one way is basically keeping these dumb and controlling injection in the boundary, such that you provide quality of service by controlling how much each core can inject into the system. And if you find out that this core is behaving not so nicely, meaning that it's hogging resources that some other core needs, basically you tell this core, okay, back off. You basically control the injection. This is called source throttling, and we're going to actually see examples of it later on. But this is a very different approach, fundamentally different approach, right? You don't have any control in the resources, but you have mechanisms to understand what's going on in the resources and control the injection of the cores into the resources, or control the injection from the sources into the resources. Make sense? And you can think of internet. Actually, all of these system concepts appear at the large scale as well. For example, this could be a communication network. It could be the internet. And if some core is hogging the internet, you basically tell it, stop hogging the internet, right? Stop hogging the network. This congestion control is applied in internet protocols today. TCP/IP, for example, has sophisticated congestion control mechanisms. So internet is a good example. But inside, actually, if you look at the internet, there are routers. And these routers also have quality of service mechanisms internally. So internet is a combination of smart resources as well as dumb resources at the same time. And that's going to be true for the systems that we're going to look at as well. Okay, so how do we change it back? Okay, thanks. So that's one example. The other example, can you see it? I think one light is still there. Is it good? It was a little bit darker before. I cannot see it very well. Okay, that's much better for me. Is it good for you also? Okay, cool. Okay, that's one example. It's basically source throttling to control access to the memory system. Another example could be you partition the resources somewhat. Even though they're shared, you partition it internally such that you reduce the interference as much as possible. So this is, for example, you map the data of applications that interfere badly to different memory controllers. Now they don't interfere in the memory controller, at least. So that's very different from smart resources. You basically perform data mapping, and your memory controllers can still use first ready, first come, first serve, which is fundamentally unfair. Right? But because you partitioned your data nicely, the applications that would cause unfairness problems to each other are not interacting with each other anymore in the memory controller. So resource is dumb, but you do something smart by doing data mapping smartly. Or you could do thread scheduling smartly, meaning that if you know that applications do not destroy each other's performance when they run together, maybe you schedule only those applications together. And other applications that destroy each other's performance, when they're scheduled together, they're separated to different cores. Of course, this requires you to have flexibility in your scheduling and many applications. If you have only 4 applications and 4 cores with different applications with different requirements, then you may not be able to do this all the time. But this is another example of you can still keep the resources as they are today. Make sense? And we're going to look at these 3 approaches also. But keep in mind that you can actually combine both of those. You can still keep the resource. You can make the resources smart, and you can also do all of these. So we're going to talk a lot about quality of service of our memory controllers in this lecture, especially. We'll see how much we can finish, but we're going to touch upon a lot of these issues. But before I go into that, I'll also give you fundamental interference control techniques. We're going to talk about 4 different techniques. The goal, again, is to reduce and control interference in the memory system, but these are actually beyond the memory system also. So there are 4 ways of doing this. One is prioritization or request scheduling. You schedule the request such that you can reduce or control interference, and we're going to talk a lot about that. The second is data mapping. We discussed this. By doing your data mapping intelligently across controllers, banks, channels, ranks at different granularities, you can reduce the interference or control the interference. That's actually true for the large scale also, right? So if by partitioning your data across your servers that are serving requests, let's say search requests, you can ensure that one server doesn't get loaded as much. The request that can go to multiple different servers because you've mapped your data nicely, right? Okay, or you can replicate your data as well, right? So the third one is core source throttling, which we discussed over here. You throttle the sources or the cores such that you can reduce interference or control interference. One of the advantages of this will be you actually reduce the load in the system because not all cores are injecting as heavily. And reducing the load can actually make life easier, meaning that you don't saturate the resources. And the last one is application thread scheduling or thread scheduling, and we're going to talk about that as well. So we basically discussed this in the previous slide, but I wanted to make this more clear. These are 4 fundamental techniques. Whenever you're trying to do quality of service, you have all of these options normally. And this is not just specific to the memory system, this is specific to pretty much everything that we see. You can actually apply it to human life, but I don't want to go through that right now. Prioritization is one example, and that's very easily applicable to human life, right? Data mapping, you can partition resources between different people such that people who interfere badly with each other when they need a resource don't actually try to access that resource at the same time, right? Okay, anyway. Okay, so we're going to look a lot into quality of service over memory scheduling. This is actually a really important part of the memory system as we discussed. And it is a bottleneck, as we know. Basically, memory controller resolves memory contention by scheduling requests. And the key questions that we're going to try to answer is how do we schedule requests to provide high system performance, high fairness to applications, and also configurability to system software. We're going to look into this some, but the papers have a lot more detail about that configurable system software. So if you want to do something like this, the memory controller somehow needs to be aware of the threads. So today this is not becoming an issue anymore, but there used to be some time where the thread IDs from the cores of the requests, thread IDs of the requests that were basically the hardware context IDs that generated the requests were not being communicated to the memory controller. I think this is not that hard. You just add a bunch of wires, right? Or something that is part of the packet that specifies, okay, this is the hardware context ID that generated the request. So that's all you need to go into the memory controller. Okay, I'll give you an evolution of this, although probably I'm not going to go through these slides. You may want to go back to these slides in a little bit. This is what we're going to cover. Not everything. We're not going to cover everything. So basically, when we first started, this is the first idea that we're going to cover. But this is a very good summary of, I think, a bunch of different ideas. So I'm going to leave you with this. You can take a look at it as a summary. Basically, it's a key summary with one sentence of each of the works. But we're not going to cover all of these, actually. And we may get back to the slide at the end, these set of slides at the end. Okay, let's start with the first one over here. This first one is interesting because when we first realized the problem of slowdowns, unfair slowdowns in memory, what is the first thing that comes to your mind? Well, this is the first thing that came to our mind. You see this, you see unfair slowdowns, this slowing down by 5%, libquantum slowing down by 5%, and this application slowing by 8x almost. And you realize there's an uncontrollability problem, and you want to solve it by making the memory system more fair. The question is, what is fair? Well, one definition of fairness could be, okay, wouldn't it be nice if actually everybody slowed down by the same amount, right? Which is not a bad definition, actually, because that enables proportional slowdown for everyone, so no one is left behind in a sense. So that's the idea over here. It's called stall time fair memory scheduling. And the goal is the threads that are sharing the memory system should experience similar slowdowns compared to when they run alone. And that's the definition of fairness in this work. The system is fair if the slowdowns of the threads compared to when each of them is run alone is equal. And there is, of course, a basis to this because you're really trying to ensure proportional progress across the different cores. And what is the proportional progress? There's a baseline for each application, and you're not slowing that application very disparately compared to other applications. And also, this improves overall system performance by ensuring cores make proportional progress to each other. So how do you actually do this? The memory controller estimates each thread slowdown due to interference and schedules requests in a way to balance those slowdowns. And we're going to look at that. It's not an easy thing to do, actually. We're going to look at how to actually implement it after some insights that are developed in 6 years time frame after this. But if you actually try to do this, what I'm going to describe, it's not easy to implement. It's a very interesting, very cool idea, I think, but this is not easy to implement in real hardware. So basically, let's go a little bit more into the definition. So we define a DRAM system to be fair if it equalizes the slowdown of equal priority threads. Assume that these threads are equal priority. If they're not equal priority, then we're going to talk about that. Well, we may not have slides on that, but the paper definitely discusses that. Equal priority means equal slowdown. Of course, relative to when each thread is run alone on the same system. So how do we do that? Basically, we define a DRAM-related stall time to be the time a thread spends waiting for DRAM memory. And there are two stall times. You have stall time shared. This is the thread's DRAM-related stall time when it runs together with other threads. And stall time alone. This is the thread's stall time when the thread runs alone on the same system. And the memory slowdown of a thread is defined as stall time shared divided by stall time alone. Hopefully this is simple. And this is the relative increase in stall time. So basically, if a thread is running together, running alone, it has a memory stall time alone of 1 second. When it runs together with some other thread, its stall time increases to 4 seconds. Its slowdown will be 4 divided by 1, 4. Right? And the goal of the stall time fair memory scheduler is to equalize the memory slowdown, this value for each thread, without sacrificing performance. And the good thing about this is it considers the inherent DRAM performance of each thread. There's a baseline that you divide by, ST alone. You don't want to just equalize the stall times, right? Because threads have extremely disparate requirements in terms of memory. You want to look at the baseline. By looking at the baseline, you aim to allow proportional progress of the threads. Okay, so how do you actually implement this? This is an algorithm. How do you implement this algorithm in hardware? So it's not easy. For each thread, the DRAM controller tracks stall time shared and estimates stall time alone. Stall time shared is relatively easy because you're actually looking at how much time the thread is spending waiting for DRAM when it's running together with other threads, right? So you look at whether the thread can continue finishing instructions in its core. If it cannot, then you increment a counter. That's not that hard. But this is the hard part. Actually, this is the fundamentally hard part in all of the quality of service mechanisms. How do you estimate the performance of a thread when it's running together with other threads, but the performance that you're trying to estimate is the performance that you would get alone when it's not running together with other threads. Basically, we would like to get stall time alone, but the thread is running together with other threads. How do you estimate that stall time alone? Well, one way is saying, okay, I'm going to deschedule other threads and run this thread together, run this thread alone for some time. Now there are multiple disadvantages to that. Basically, you lose throughput while you're trying to do this estimation. That's one problem. The other problem is you're getting the stall time alone, but you're not comparing it to a stall time shared that's measured at the same time, right? For the same time frame, for the same instructions. So that's the problem. So that's why we want to do this online without descheduling some other threads. Actually, that approach doesn't work too well because of both reasons. So what the DRAM controller does in this case is it computes a slowdown value for threads that have legal requests. Legal request meaning that a request that can be scheduled. So it computes stall time shared divided by stall time alone for each thread. And it computes an unfairness value. So I'm assuming right now that you know how to do the stall time alone estimation. Actually, let me pull back. I don't have a slide on that, I think. No, I don't. So how do you estimate stall time alone? So it's not easy to do it in the memory controller. And the approach in this paper is actually relatively complex. Basically, the approach that's taken in this paper is you know the stall time shared of the thread because you can compute it while the thread is running. Some of that is because of additional excess stall time that's caused by other threads' requests interfering with this thread. So if we can somehow guess how much time is the excess stall time, extra stall time that's caused because of interference, we can subtract that value from stall time shared and get stall time alone. Basically, stall time alone is equal to stall time shared minus some stall time excess. right? Extra stall time. So then the key question is how do you figure out that stall time excess? It's not easy again. Basically, there are cases where you can figure this out somewhat. If a thread's request is delayed, if the memory controller cannot service a thread's request because it's servicing some other thread's request to a given bank, you basically increment some counters. Increment a counter, the stall time excess counter. That's one example, right? But of course, things become more complex because of interference. So let's say, how do you take into account a row buffer conflict that's caused because of interference, but that wouldn't be there if the thread were running alone? Now that becomes a bit more hairy. You need to now keep track of the row buffers. And you need to keep track of the row buffers that would have been open if the thread were running alone. You could do that. Okay, you add some more row buffers or shadow row buffer IDs, at least addresses. These keep track of the row buffer ID that would be open if the thread were running alone in the system at additional hardware cost. And whenever you schedule a request from this thread, you check, you check whether it's a row buffer conflict. If it's a row buffer conflict, but if it wouldn't have been a row buffer conflict if the thread were running alone, you basically increment stall time excess by some amount. That some amount is actually how much additional time you delay the thread because of the additional row buffer conflict you get. So, okay, you account for some more cycles. That's good. So you could keep doing that, but you need to be able to do this for every source of interference if you want to get ST alone or ST excess absolutely correct. And there are many, many forms of interference, as we know in the memory controllers, as we talked about earlier, right? Okay, another form of interference that this paper doesn't take into account is a thread is doing, let's say, a lot of write requests, and some other thread is doing a lot of read requests. Because this thread is doing a lot of write requests, this thread's read requests get delayed because this thread forces the memory controller to switch into write mode. Because you can only schedule writes and reads, writes or reads. You cannot do both of them at the same time because there's a write to read switching penalty, as we know in DRAM, right? So how do you take that into account? Easily. You could add some more counters, but it becomes very hairy actually to perfectly estimate this ST excess. And also, you could add the counters to count how many additional cycles this particular request is delayed. There's another hairy part, which is the request, the delay that this request incurs doesn't necessarily impact your stall time by the same amount, right? Because of memory level parallelism that we discussed. This thread may have one request that's delayed by 50 cycles. It has another request that's delayed by 25 cycles. Now, because of memory level parallelism, some of the delay may be hidden, right? But how much is it hidden? How much would these requests would be scheduled in parallel when the thread was running alone, if the thread were running alone? That's very, very hard to really perfectly guess, unless you're completely simulating what would be happening if the thread were running alone, which you really don't want to do. That's very expensive, right? So alone time estimation is, because of this, very complex, because the interactions between threads are extremely complex in a modern memory system. But assume that you estimate it in some way, and this paper proposes some way. It ignores a lot of the interference. As a result, the estimation is not correct completely, but it may give you a good idea in terms of fairness. That's the idea over here. You estimate this somehow. You estimate the slowdown of the thread compared to when it's running alone, and you compute an unfairness value in the memory controller. And the value basically says, take the maximum slowdown that I see for any thread in the system divided by the minimum slowdown that I see for any thread in the system. And ideally, if our goal was what I suggested before, to equalize the slowdown, this unfairness value should be equal to 1. Right? Okay, if the unfairness value is less than some software specified threshold, in this case it's maximum tolerable unfairness, then that's good, everything is good, and the memory controller uses the DRAM throughput oriented scheduling policy that we use today, FRCFS, let's say. But if unfairness is greater than some tolerable threshold, alpha, let's say, then the memory controller uses a fairness-oriented scheduling policy where it basically prioritizes the request from the thread that has been slowed down the most. And all else being equal, it prioritizes row hits, and all else being equal, it prioritizes oldest first. Basically, this is the fairness. You want to minimize the slowdown or reduce the slowdown of the thread that has been slowed down the most, and that's how you do it. This is a simple way of doing it. Of course, you could design more complicated mechanisms to balance the slowdowns, right? Then the key question is, how do you define this alpha? Well, you want to define an alpha such that you have some breathing room. Usually alpha is about 1.05 or 1.10, but of course this depends on how much unfairness you're willing to tolerate in the system with this definition of unfairness. Okay, so let's take a look at how this works. I'll give you an example from 2 threads. This is random and stream, I believe. Basically, you need to have slowdown counters for each thread, and you need to have stall time estimation counters, which are not shown here. And there's an unfairness is basically the division of these, max divided by min, and the alpha value, let's assume, is 1.05. So initially, unfairness is tolerable. It's less than 1.05. So the memory controller starts using the throughput-oriented scheduling policy, row hit first policy. It schedules requests from the blue application, T0. And then it keeps doing this for some time. And now, red application at a request, the blue application request is prioritized over the red application. So T1 slowed down a little bit because the memory controller chose this application request over this application request. As a result, T1 slowdown increases and unfairness increases. Right. Now, but unfairness is still tolerable, so the memory controller keeps using the row hit first scheduling policy. And then this happens, memory controller schedules this request over here, and it increments the counter saying T1 was delayed a little bit more. As a result, T1 slowdown increases, and T1 slowdown becomes intolerable at this point, which means that the memory controller switches to the fairness-oriented scheduling policy, and the next request it schedules is not T0's request, because T0 is not the max slowdown thread in the system. It's T1's request. So it switches to T1, kicks out the row from the row buffer, row 0 from the row buffer, and that causes slowdown to T0, because T0 would T0's request would not have been delayed if this didn't happen, right? Okay, so that's the idea basically. But now the unfairness gets in check again. We cause slowdown to T0 because we basically kicked out its row buffer that would be useful. As a result, unfairness reduces below the tolerable threshold. As a result, we go back to the throughput-oriented scheduling policy. In this case, throughput-oriented scheduling policy says there is no row buffer hit. As a result, you prioritize the thread that has the oldest request. And that opens the row buffer again. That leads to some slowdown, as you see, because we are delaying this request. But still, the slowdown is tolerable. And we keep the throughput-oriented scheduling policy. But at some point, slowdown becomes intolerable again because you delayed this thread a lot, and you switch back to the fairness-oriented scheduling policy. And this keeps going on and on, as you can see over here. You keep switching back between the fairness-oriented and throughput-oriented scheduling policy, and your slowdown is hopefully, the unfairness is hopefully in check. Does that make sense? Of course, if we set unfairness to 1, we would never be able to exploit row buffer locality easily in this case. So setting unfairness to something greater than 1 is good. And the paper actually explores that value. Okay, so you can actually enforce thread priorities over here as well, and the paper basically says, okay, if a thread is higher priority, multiply the slowdown with the priority level. If your priority is really high, for example, it looks like you have a much higher slowdown than you really do. As a result, you can enforce the priorities. Priorities are not a great way of so if you look at priorities in the system, what does it mean to have a priority of 1 versus 2, right? These are actually not very well defined. It just means that a thread that has a priority of 1, or let's say higher is better, higher is higher priority. A thread that has a higher priority gets more time. But it's fundamentally not defined how much more time it should get. So we just do our best effort to incorporate priorities in there. It's actually good to think about how to have a much more fair scheduling system. That should really be based on the times as opposed to priorities that you get, or the requirements. But we're not going to go into that right now. Okay, so this is the first fair memory scheduler that takes memory characteristics into account. There were actually previous memory schedulers that were designed for, basically these schedulers took the ideas of network fair queuing and applied the ideas to memory controllers. But memory is very different. If you look at a network link, there is no row buffer and there are no banks. Which means that the scheduling problem actually in the network link is a lot easier. In memory, you have, and actually you could model that with a lot of scheduling theory concepts, because there is no state, meaning there is no locality, and there is no parallelism, there is no bank. It's just a single link that you're sending different packets on, and different flows are contending for that link. That makes it very amenable for analysis using scheduling theory, for example. It's essentially a queue. Whereas memory is much more difficult because of the existence of the row buffers as well as the banks. So this was the first algorithm for fair multi-core memory scheduling that takes that into account. Well, clearly it provides a mechanism to estimate memory slowdown of a thread. I'm going to give you upsides and downsides as we go along in these lectures. It's good at providing fairness, actually. I didn't give you results, but this actually improves fairness quite a bit compared to FRCF. I'll give you the results after the end of the next scheduler that we discussed, because that has the results for that scheduler also. So it also improves system performance, as you will see in those results. So it's not bad. Being fair actually can improve performance, because you're making cores that would otherwise be doing not much progress, be making not much progress. You're enabling them to make progress in the system. That is the reason for the performance improvement. It's not always, of course, true. Sometimes you actually reduce performance by being fair. But our goal is not fully performance in this case. Overall, on average, you actually improve performance by being fair, which is really interesting. Okay, the downsides. This doesn't handle all types of interference. This will become more clear when we discuss the next scheduler. And it's actually complex to implement. It's not easy. The concepts actually influenced a lot of works, but this is not an easy scheduler to implement, really. And slowdown estimations can be incorrect. So you could, for example, use these slowdown estimations. Let's assume that you had perfect slowdown estimations. You perfectly knew how much you slowed down this thread compared to when it's run alone. That could be a very good way of trying to provide performance isolation, right? Because you know exactly what your slowdown is. You can have a slowdown target for the thread, and you can try to reach that target. But if your estimation is really incorrect in an absolute sense, let's say you think your slowdown is 2x, but your slowdown is really 6x, then you cannot really satisfy a requirement in terms of slowdowns. That's not the goal of the scheduler. The goal of the scheduler is to provide fairness, right, with that definition. So incorrect estimations doesn't affect that goal as much. It does affect it a little bit, but it doesn't affect that goal that much. But if you really want to enforce some slowdown guarantee, you really want your slowdown estimations to be correct. And we're going to talk about that later on. Okay, so if you'd like to know more about this, this is the paper. And this may be a good place to take a break, actually. Yes, I've talked a lot about so far. We're going to move into other memory schedulers, but let's take a break for, how much time would you like? Okay, let's do it for 15 minutes today, until 1:40. And then we'll talk about a lot of memory schedulers. Okay. Okay, so now we're going to have a journey on memory scheduling, which is really fascinating. There's still a lot more to do in this area, by the way. And some of the ideas that I'm going to describe to you have made their way into, especially SOC memory controls, as I said. Okay, so we'll start with the next one. This was a lot of fun, actually. Okay, so basically this work that I'm going to describe discovers another form of interference, which is really not so good in this overall system design. In general, if a part of your system is designed for something, if another part of your system is destroying that something, then you have a problem. Basically, these two components don't work well with each other. And that's essentially the problem that we have in the design of cores and the memory controllers, as I will describe. If you look at the design of cores, these cores try to tolerate the latency of long latency memory requests, DRAM requests, by generating multiple outstanding requests concurrently. This is the notion of memory level parallelism that we discussed earlier in the course. How do you do this? You basically employ out of order execution of requests. You do have non-blocking caches, as we discussed. You employ things like run-ahead execution, as we will discuss later on. Basically, the notion is if you don't have only one request, have multiple requests and overlap their latencies. Right? This is only effective, of course, if the DRAM controller actually services the multiple requests in parallel in the DRAM banks. Now, that's the assumption in a single core system. But if you have multi-core systems, you have multiple threads that are sharing the DRAM controller, and the DRAM controllers are not aware of each thread's memory level parallelism. As a result of this, a DRAM controller can service each thread's outstanding request serially and not in parallel. If you actually don't service the requests in parallel, you don't get the benefits of memory level parallelism. Essentially, you're serializing otherwise concurrent requests. So basically, instead of stalling once for all of the requests, you're stalling once for each request, as we've discussed a long time ago, right? This is because your memory controller is really not aware of the way your core is designed. You take all the pains to design your core to generate these requests, except your memory controller serializes them in the end. Okay, let's take a look at an example for this. This is a single thread executing alone. It generates two requests. Let's say load to one bank and load to another bank. And it needs to wait. It needs for both of those requests data to return to make progress. Let's say it's going to add the two results that it's going to get from memory. So the memory controller schedules the first request to bank 0 and the next request to bank 1. So these are serviced in parallel in the two different banks. And the thread stalls while waiting for both of those requests. At some point, the first request's data returns and the second request data also returns. And the thread can compute now again. So what happened here was, because these requests went to two different banks and they were serviced in parallel at the same time, the bank latencies of the two requests are overlapped. As a result, the thread stalls for approximately one bank access latency. We're ignoring other components of the latency over here, assuming the bank access latency is the longest part of the memory latency, which is usually true, but not always, of course, right? Okay. So let's take a look at what happens with a baseline memory controller that is executing two of these threads that do essentially the same thing. They both compute, each of them encounter two DRAM requests. They send the DRAM request to the memory controller, and these are the same requests that I showed you earlier, except thread B has two different rows. It doesn't matter which row. Well, it does matter which row actually. It's not the same row as thread A's rows. So basically, the memory controller receives the request in this order, and let's say services the request in the order they arrive, and they happen to arrive in this order. So it first takes thread A request to bank 0, schedules it, and then takes thread B's request to bank 1 and schedules it, and both of the threads stall waiting for those requests. And then this request is done, its data is sent back to the core, and then the memory controller takes thread B's request to bank 0 and schedules it, and then this request is done, its data is sent back to the core, and then the memory controller takes this last request and schedules to bank 1. So even though the threads received one data element, one of the DRAM requests, they cannot continue because they're waiting for the other data element. Right? So both of them stall for a while. Until this request is done, its data is sent back, and until this request is done, its data is sent back, and then the threads can continue computation. So what happened right now was bank access latencies of each thread were serialized. As a result, each thread stalls for approximately 2 bank access latencies, as you can see it over here. Basically, each thread's requests were serialized. The key question is, can we do better? If the memory controller were aware of the different threads' memory level parallelism, it could do better, perhaps, by actually trying to preserve that parallelism. And that's the idea in a parallelism-aware scheduler. Both threads generate the requests again, and let's take a look at how the parallelism-aware scheduler behaves. It first takes, let's say, thread A's request to bank 0 and schedules it. And then it realizes that thread A has another request to bank 1. And if that request is scheduled to bank 1, both of these requests will be overlapped in terms of access latency. So the memory controller, instead of taking the next request over here or some other request, it takes thread A's request to bank 1 consciously to maximize the bank level parallelism of that thread. And this thread is waiting for requests, and both threads are actually waiting for the requests, and they both stall for a while. Then the memory control, this request is done. The memory controller takes thread B's request to bank 0, schedules it, and then it takes this request is done and takes thread B's request to bank 1 and schedules it. Now what happened is, once these two requests are done, at this point, this thread A can continue computation because both of its data elements came back from memory. This thread B cannot continue computation until both of its requests are done, and they're done at this point, basically. The good thing is we saved a lot of cycles over here because we enabled thread A to make progress because we parallelized its requests as opposed to serializing them. Actually, both of threads, memory level parallelism or bank level parallelism, was preserved in this case, except this bank level parallelism was preserved a little bit later over here. So this thread didn't gain performance, but it didn't lose performance either by doing this reordering. So this is very powerful, as you can see, which means that we reduce the average stall time, the red parts, across both threads to 1.5 bank access latencies as opposed to 2 over here. And that's the idea over here. And we didn't do something that go against what the core really generates. So the idea is very simple. So the first principle I already gave you actually. The parallelism-aware batch scheduler works based on 2 principles. The first principle is you want to reduce the interference that happens because of two threads running together, interference that happens in the bank level parallelism. And if you want to do that, you want to be parallelism aware, which means that you want to schedule requests from a thread to different banks back to back. If you picked a thread to schedule to bank 0, pick that thread to schedule into bank 1, into bank 2, bank 3 if it has requests. That's the idea. Now this is good because it preserves each thread's bank parallelism as much as possible, but this can also cause starvation. Now you're prioritizing one thread in all banks. So if the thread's request gets serviced quickly, it can generate other requests. That thread can now hog the memory system, and we don't want that hogging. So the other principle is called request batching. And the idea over here is to prevent that sort of starvation. You group a fixed number of oldest requests from each thread into a batch, and you service that batch before all other requests in the system. And you form a new batch when the current one is done. And the memory controller operates this way. If you do this, you eliminate starvation and you provide fairness. You ensure that the batch is prioritized over everything else. It makes forward progress, and everything gets batched at some point in time. That's how you eliminate starvation. And this is very powerful. It's actually implemented in many SoC controllers today. And also, now within the batch, you're more flexible. What you can do within the batch is you allow parallelism awareness within the batch. But as you will see that, you can do anything inside the batch. So let's take a look at this example. Basically, you have 4 threads. Each of them has 2 requests, these 2 different banks. You form a batch somehow. You don't wait to form the batch. The batch happens naturally. While you're serving some requests, there are some requests that are waiting, and you form the batch based on the requests that are waiting in the memory controller. We will see that in a little bit, actually. So you don't actually delay any request to form the batch. That is not good in general, although there could be cases where you may want to delay requests also, but that's a bit dangerous. Okay, so the memory controller basically first takes thread 0's requests and schedules them in parallel in the banks, and then there are some requests that are arriving from thread 2 into the memory controller, but they're not part of the batch because the batch is already formed. And then it takes thread 1's requests and schedules them, and then it takes thread 2's requests inside the batch and schedules them, but the requests that are outside the batch are not scheduled to ensure that thread 2 doesn't starve all of the other threads. And then it takes thread 3's requests and schedules them. And once this batch is done, once there is nothing left in the batch, it forms a new batch. And as you can see, there's thread requests that are already waiting, and that's how you naturally form the batch. So that's the idea at a conceptual level. Okay. So basically, there are 2 components to this. One is request batching, and the other is within batch scheduling. Request batching is relatively simple. We'll take a look at that. Actually, both of them are relatively simple, but this tends to be much simpler. So basically, each memory request has a marked bit, has a bit associated with it saying, is it part of the batch? Is it part of the oldest batch? So when you form the batch, you mark up to some marking cap, oldest requests per bank for each thread. This is a threshold, which we will discuss later. And the mark requests constitute the batch. And you form a new batch when no mark requests are left. Mark requests are prioritized over unmarked ones. That's how you ensure that the batch is prioritized over everything else. Which means that there is no reordering of requests across the batches. There is no starvation, which means that there's no starvation, which is good. And this also provides a substrate for high fairness. Although fairness depends on what you do inside the batch as well. But this gets you to a good baseline for fairness by eliminating starvation. Okay, so then the next question is, how do you prioritize requests within this batch that's formed? And within batch, actually, now you have a lot of freedom. You got rid of starvation in the system by ensuring batching. Within the batch, you can do anything, but we want to do particular things. So you can actually use any DRAM scheduling policy. You can use FRF-CFS, which is good for row buffer locality. Or you could use something else that preserves intra-thread bank parallelism. Actually, in this case, we want to preserve intra-thread bank parallelism as well. If you want to preserve intra-thread bank parallelism, you want to service each thread's request back-to-back. So to be able to do this, this paper introduces computing a ranking of threads when the batch is formed. So we'll talk about this ranking. But basically, higher ranked threads are prioritized over lower ranked ones. And you form this rank such that one thread, this enables that the requests from one thread are serviced in parallel across different banks. Because all of the banks actually obey this ranking. If thread 0 is prioritized in this bank, it's prioritized in the other bank also, and in the other bank also. And you could actually extend this ranking to different memory channels, memory controllers. Basically, different threads are prioritized in the same order across all banks because everybody's aware of this ranking. So that's the idea. So now the next question is, how do you form this ranking? Let me give you the benefit of ranking first before how we form the ranking. Basically, the problem is if you don't rank the threads, so you have this issue in bank 1, thread B's request is prioritized, and bank 0, thread A's request is prioritized. As a result, both threads stall for 2 bank access latencies in this example, right? And that's the memory service timeline over here. Now, if you form a ranking, rank thread A higher than thread B, and ensure that both banks obey that rank, essentially what you're doing is changing the prioritization order such that threads are prioritized in the same order across different banks. And if you do this, what happens looks like this, which is very similar to what I showed you earlier. You save cycles on thread A without introducing additional cycles on thread B, which is good for performance. Okay, so ranking scheme actually affects system throughput and fairness. We want to maximize system throughput and minimize unfairness. Again, we're going to use the same definition of unfairness. We're not changing it yet. We're going to try to equalize the slowdown of equal priority threads, assuming everything is equal priority for now. So if you want to maximize system throughput, you really want to minimize the red parts that I showed you earlier, minimize the average stall time of the threads within the batch. It turns out if you want to minimize unfairness, it's a similar goal. You would like to service threads with inherently low stall time early in the batch. It's posed differently, of course, right? Basically, this is what I said earlier. If a thread doesn't have a lot of requests or a lot of stall time to begin with, don't delay it that much. Because if you delay it, so let's assume that the stall time of the thread when it's running alone is 1. The stall time of another thread that's running alone is 100. You would like to equalize the slowdown of the thread somehow over time. If you delay the first thread by 1 time unit, its slowdown becomes 2. If you delay the second thread, its slowdown becomes 101 divided by 100. Basically, if you delay a memory non-intensive thread by the same amount that you would delay a memory intensive thread, you have a much worse impact on the memory non-intensive thread, because memory non-intensive thread doesn't stall that much to begin with, and you're delaying it by the same amount. So the insight is this: don't delay the memory non-intensive threads that much, prioritize them inside the batch. Because, as I said, delaying memory intensive threads doesn't affect fairness as much. It doesn't affect performance as much also. Okay, so that's the idea. If you actually want to realize this, it turns out both of these benefit from shortest stall time first ranking. This is also called shortest job first. It's an example of shortest job first. So if you want to maximize throughput, there's actually a lot of theory on this. This is part of the scheduling theory, which I'm not going to go into. You can read the next paper that I'm going to discuss that goes a lot into scheduling theory. But basically, if you have a single server queue, let's say, like a factory, and if you want to maximize your throughput out of that factory, you really want to finish the shortest jobs first. That overall maximizes your throughput. And you can read this paper actually that talks about the factories related to this. So this works really well. You can prove things about this if you have a single server queue. That's FIFO. Well, that's not necessarily FIFO, but that's a single server queue. There's no locality, there's no parallelism. You have a link, basically. Then prioritizing the shorter jobs gets you the highest system throughput. In this case, it's a very different thing, but it turns out the insight works nicely as well. We'd like to estimate what is shorter. Basically, the control estimates each thread's stall time within the batch, and it ranks the threads with shorter stall time higher. I'll give you an example of this to make a concrete sense of it. So basically, this is what we're going to do, and I'm going to give you an example of it. We're going to estimate threads with shorter stall time by counting their requests. We were going to count the maximum number of mark requests to any bank that each thread has. We're going to call that the max bank load of the thread. And the longer this is, the higher the stall time of the thread is, likely. Basically, we would like to rank threads with lower max bank load higher because we want to prioritize the threads that have lower stall times. That's the first thing. The second thing is a tiebreaker. Basically, assuming two threads have the same max bank load, how do you break the tie? We basically also look at total number of mark requests, which is total number of requests that are in the batch belonging to this thread across all of the banks. We'll call it the total load. So, and this is a tiebreaker. As I said, you rank the thread with lower total load higher. So let's take a look at an example, a concrete example of this. So these are 4 different threads. We're going to ignore the row buffer locality. The paper is an example with row buffers. It's good to see that, actually. But the row buffer complicates things a little bit. But we're going to ignore the row buffer in terms of the computation of this, because that makes the computation worse. Basically, let's compute the max bank load and total load of these different threads that happen to have these requests that are queued up in front of these banks. So let's take a look at thread 0 first. Thread 0, if you isolate its requests, the maximum number of requests it has to any bank is 1. So its max bank load is 1. Its total load is 3. Right. Okay. Thread 1. The maximum number of requests it has to any bank is 2. It has 2 requests to bank 0, 1 request here, 1 request here. As a result, its max bank load is 2, and its total load is 4. Thread 2, the maximum number of requests it has to any bank is 2, and its total load is 6. And thread 3, the maximum number of requests it has to any bank is 5, and its total load is 9. And now we can form a ranking between these threads. Max bank load is lowest here, so thread 0 is ranked higher than thread 1. Tiebreaker, thread 1 is ranked higher than thread 2, and thread 2 is ranked higher than thread 3. So that's the idea. That's going to be our scheduling order that we're going to use. Okay, so let's take a look at the stall time of the threads with the baseline scheduling order first. Baseline means first, oldest first in this case, and assume that the threads that are over here are older. So this is the time of the scheduling. I'm going to simplify things, assume each request takes one time unit. So let's assume, let's take a look at the stall times of each thread. The stall time is dictated by the last request that is serviced, the service time of the last request, or for a given thread. So for thread 0, the last request is serviced after 4 time units. So its stall time is 4. For thread 1, the last request is serviced also after 4 time units, so its stall time is 4. For thread 2, last request is serviced after 5 time units, so its stall time is 5. And for thread 3, last request is serviced after 7 time units, so its stall time is 7. And if you average these stall times, which gives you an indicator of overall throughput, let's say, you get 5 bank access latencies. On average, a thread stalls for 5 bank access latencies, or 5 time units. Okay, well, we were trying to do better, right, by preserving parallelism. The scheduling order within this batch, using the PAR-BS scheduling order, is going to look like this. Basically, we're going to rank the threads with the heuristics that I told you earlier. And the heuristics led us to rank T0 higher than everything else, which means that we first schedule all of T0's requests that are queued up. Now, if you do that, T0's requests are serviced in parallel in bank 1, bank 2, bank 3. And this is what you get. Basically, T0's requests are scheduled in the first time unit, and they're done in the first time unit, and you preserve its parallelism perfectly. So its stall time is 1. Then T1's requests are prioritized over T2, which means that T1's requests are scheduled like this. It's like forming a Tetris. because in the first time unit, T0 doesn't have request to bank 0, T1 has request to bank 0. As a result, it's prioritized, right? And its last request, T1's last request is serviced after 2 time units. As a result, its stall time is 2. Then T2's requests are prioritized over T3, and its requests fall into this Tetris thing, like this. Because basically it gets delayed by T0 over here, it gets delayed by T1, T0 and T1 in all of the other banks. As a result, the requests are scheduled this way. And T2's last request is serviced after 4 time units. And the last priority belongs to T3, and T3 happens to be scheduled nicely this way. So as you look over here, this looks very much more regular as opposed to this mess that you see over here. You preserve the bank level parallelism of each thread as much as possible. Of course, it's not perfectly possible because there's interference between different threads. And you do it in a manner to maximize the progress of the thread that has the lowest stall time. And if you actually average these stall times that you get after all of this, you get 3.5 bank access latencies. So for this particular batch, you get a 30% reduction in stall times. This doesn't directly translate, of course, into performance improvement because there are other batches potentially, there are other requests that are waiting up there that we ignored because we were looking at this batch for now. So the real performance is much more complicated. It's a dynamic scheduling mechanism, so it's very hard to enumerate all of this. Okay. Okay, so basically that's the insight. And we would like to realize it. How do you realize it? So this is a simple scheduling policy. Remember, we want to prioritize the batch request first, which means that mark requests are prioritized over everything else. And within the batch, among the mark requests or among the non-mark requests, this is the prioritization order. You prioritize row hit requests to maximize row buffer locality. The next priority order, higher ranked thread, is prioritized over other threads to maximize parallelism, and then everything else being equal, you prioritize older requests over others. Now you could argue, okay, why didn't we prioritize higher rank before the row buffer locality? That's a tough choice. The paper actually explores it in detail. It turns out this provides you a little bit more performance. There's always, unfortunately, this, and you will find that this is usually the case, not just in the memory scheduler, but there's always a tension between locality and parallelism. If you want to maximize locality, your parallelism may get hurt. And if you want to maximize parallelism, your locality may get hurt. And this is one instance of that trade-off over here. If you prioritize row buffer hits, you're basically not taking into account this ranking of the threads, which really leads to the parallelism. In the same level, you would be taking that into account if you actually use that as the higher priority. So that's the difficult part. Maybe there's a better scheduling mechanism, but the paper doesn't look into that. Okay, so it turns out the scheduling policy works best within batch scheduling and overall performance. So this has 3 properties. It exploits both row buffer locality and intra-thread bank parallelism. Not perfectly maybe, but it does exploit both, and you do want to exploit both. It's work conserving, meaning that it doesn't waste bandwidth. So if there is a request waiting for a bank that's available, that request gets scheduled. Basically, if there are no mark requests, unmarked requests are served into the bank that they're trying to access. Right? This is just a prioritization order, basically. There is no delay that's induced because of this or because of batching. So unmarked requests are still served if they can be served. And the last one is marking cap is important. Remember, marking cap determines how many requests are marked for a given thread to a bank when you have no requests, no marked requests in the system. So now this leads to an interesting issue because that determines how many marked requests that you have for a given thread. If you have too small a cap, if you are very conservative in marking the requests, you may not exploit row buffer locality very well. If you have too large a cap, what happens is you have too many requests inside the batch. Now your batches are much larger, which is good for exploiting row buffer locality, good for exploiting parallelism, but it's not good for memory non-intensive threads. It's not having larger batches is not necessarily good for your fairness or sometimes performance because your batch is very long and your batch is prioritized before any other request. if you have a memory non-intensive thread that injects a request, now it needs to wait for all of the requests in the batch to be serviced first. Because only after that this request can be scheduled. Or it gets lucky and it goes into a bank that has very small number of requests that are marked. So you basically inherently penalize these memory non-intensive threads if you do this batching and batches are large. And that's actually the Achilles heel of this sort of scheduler in general. Batching is a concept that's employed, but unfortunately, it has this unfortunate property. And the paper tries to fix this problem if you read it. We try to, for example, sneak in some of these requests from the non-intensive threads into the batch, but there's no good way of doing it after you form the ranking. So you need actually a much fluid way of handling this, and I will show you a much more fluid way later, as we will see when we talk about the Bliss memory scheduler. So here you form the ranking, and your ranking doesn't change, and your batch doesn't change until the batch gets drained. So you either form small batches, which destroys your robo for locality and parallelism exploitation, not good, or you either form large batches and that destroys the performance for memory non-intensive threads, and that has effect on overall performance and fairness as well. And there's, of course, one value that's good, as you will see in the paper, but it's not very fluid in terms of how it adapts to the behavior of the threads. You really want a scheduling mechanism that adapts very quickly to changes in the behavior of threads, and we will discuss that. It's going to be much simpler than this, but now I'm foreshadowing as to why it potentially works. Okay, so there are many more trade-offs that are in the paper that I'm not going to discuss over here. So this actually turns out to be much simpler to implement compared to what we discussed earlier, stall time fair memory scheduler. You're not trying to figure out the slowdowns of different threads. You basically use some heuristics to decide which thread to prioritize, right? So there are no complex operations. Stall time fair memory scheduler actually requires some complex operations. Of course, you may not really have a divider. You may actually implement it with lookup tables, but still it's a complex operation. And this is not on the critical path, although we will later see that this scheduler is still slow compared to some simpler schedulers. Okay, so I promised you some performance results. Actually, this is a fairness result. I'm going to give you some. So this is basically results for 5 different schedulers. FRF-CFS, you know, first come, first serve is basically a FIFO scheduler. Network fair queuing is what I mentioned earlier. You apply network fair queuing principles to DRAM without taking into account the special characteristics of DRAM. Stall time fair memory scheduling and parallelism-aware batch scheduling that we just discussed. And this is unfairness averaged across many workloads. I don't remember how many, but I think there are more than 100 over here in the 4-core workloads. So as you can see over here, FRF-CFS is very unfair, averaged across many of these workloads. FCFS is actually not so bad over here, but it becomes unfair as you increase the number of cores. And network fair queuing is also not that great because it doesn't take into account DRAM characteristics. Stall time fair memory scheduling is not bad in terms of fairness. It is best before PAR-BS, and PAR-BS is better in terms of fairness compared to STFM because it uses better techniques. And you can read the paper for more analysis. So we're getting close to 1, as you can see, but we're not 1. And as you can see, as the number of cores increases, all of these techniques degrade in terms of fairness. So they're not as scalable, although it's not terrible as well. Okay. So these are improvements of PAR-BS compared to STFM, because this is taken out of the PAR-BS paper presentation. Okay, let's take a look at performance. In terms of performance, this is harmonic mean speed up. You can take a look at the paper for what it is. It's basically a competitive ratio. You basically look at the speed up of each core compared to when it's run alone. It's actually a slowdown, and you basically add the harmonic means of those. Maybe we can take a look at the multi-core metrics later, but take a look at it. If you have multi-program workloads, how do you measure performance becomes important, and you need to actually have some way of taking into account each application's performance compared to when it's run alone on the system. Otherwise, you cannot just add up instructions from different workloads, right? Ideally, you would like to look at the execution times of all the workloads, but you cannot simulate workloads for a really long time as well. Okay, so let's take a look at the performance. Basically, this is first ready, first come, first serve. That's normalized. First come, first serve, actually, in this case, it's better. It's worse over here. Network fair queuing tends to be slightly better. And STFM actually improves performance compared to previous ones, and Power BI actually improves performance even more. So where is the performance improvement coming from? Well, certainly fairness provides you some performance improvement. Being fair actually improves performance because you're not starving some cores for a long time. You're making better progress, more proportional progress across the cores. That's one of the big reasons. That's actually one of the main reasons why STFM improves performance. All of these previous schedulers are not really fully fair. Even though network fair queuing tries to provide some fairness, it's really a partitioning mechanism in terms of bandwidth. It's not taking into account the baseline performance of each application. As a result, it's not as fair, or as high performing, as well as fair. STFM improves fairness as well as performance, and there's another reason why parallelism-aware batch scheduling is improving performance, because it's preserving the bank level parallelism of the threads. It's basically reducing the stall time of the threads significantly. Okay, so overall these are the performance improvements average across many applications compared to STFM, but overall performance improvements are relatively high, as you can see. It's on the order of 30 to 20% or so. Okay, so we're done with the second scheduler, and there are upsides and downsides of this. Upsides, this is actually the first scheduler that realizes that what you're doing in the memory controller contradicts what you're doing in the cores. And in terms of bank level parallelism, you're basically destroying the bank level parallelism that you're working hard to generate in the cores. It's a simple mechanism compared to STFM. It's not as simple as we would like, as we will see in a little bit, although we're going to get more complex before we get simpler. Batching provides fairness, and it's a very good substrate for building scheduling mechanisms in general. Although, remember, batching has a problem, which is how do you determine the size of your batch? That's actually the Achilles heel of batching mechanisms. And ranking is actually another good idea. It enables parallelism awareness, but we will see that it's going to increase our complexity. So we're going to try to get rid of that also later on. Okay, but it's really an exploration, and some of these good ideas are already implemented, but you always learn more as you keep generating ideas in research. So we will actually deconstruct some of these things. We're going to get rid of both batching and ranking, and we're going to see that one of the best schedulers that's really simple doesn't employ either of these. Okay, so the downsides of this is actually what we just discussed with marking cap. This doesn't always prioritize the latency-sensitive application. If a latency-sensitive application generates a request, it gets stuck behind the batch. Now, we're going to tackle this problem next in a different way. Basically, we're going to get rid of the fairness constraint that we have. I'm going to go through this relatively quickly. Okay, so this is the paper. You can take a look at it. It's fun to read, I think. It's also dense. Okay. So let's talk about the next one. The next one I'm not going to cover a lot, but basically this is trying to solve the problem of these memory non-intensive threads not being prioritized. And okay, let me give you the one. Basically, the goal here is to maximize system performance. We said, okay, maybe we should take a step back and ignore fairness for some time. What would you do to design a memory scheduler that would maximize overall system performance when you're running multiple applications together and they're interfering with each other? And the realization is that if you would like to maximize system performance, you would like to prioritize a thread that has attained the least service from the memory controllers at a given time. That's why this is called ATLAS, Adaptive Per Thread Least Attained Service Scheduling. What does that mean? If you actually schedule a thread in the memory controller, a thread's request, you increased a counter called attained service count. Maybe you do it per cycle or per request. We do it per cycle. So if a thread has accumulated a huge attained service count, by nature it's really used up a lot of bandwidth, a lot of memory service. As a result, it naturally gets deprioritized with this mechanism. So this mechanism prioritizes the threads that have not attained a lot of service from the memory controller. And there is a reason behind it. The reason is based on scheduling theory, but we don't have a lot of time to cover it. It's actually very nice, fascinating, but unfortunately we don't have, if we cover all of the memory schedulers in detail, we will not have time until the end of this course for anything else. But take a look at the paper. So I'll give you the intuition. The intuition is that basically you have threads that are relatively light, and light threads by nature don't really use a lot of service from the memory controller, and you would like to identify them with a simple mechanism. And this simple mechanism is counting how much service each thread has received from the memory controller. That's one intuition. There's another intuition that's also provided in the paper, but I'm not going to go into that. And this enables a mechanism now that helps you rank the threads based on attained service in the past time interval. So this operates based on intervals. During this time interval, you figure out how much service each thread has attained, and based on those counts, this is actually very simple if you think about it. It's a per thread count. You count how many cycles this thread attains service from the memory. And you have some numbers, one number for each thread at the end of the interval. And you basically rank those numbers, and you basically form a ranking across the threads where the thread that has attained the least service with the smallest counter is highest rank, whereas the thread that has attained the most service is the lowest rank. And the next interval, you enforce that ranking in the memory controller, and you prioritize based on that ranking. Okay, that's what I just said. So why does it work? Basically, this prioritizes the light or memory non-intensive threads that are much more likely to keep their cores busy. And it turns out this is actually the best scheduler in terms of performance so far at this time. And this basically shows an example of that. This is in a 24-core system with different number of memory controllers, varied. And this is the system throughput measured as the sum of slowdowns of the threads. It's called speed up, but it's really the speed up that it's really the performance that you get compared to when you run alone on the same system. And you sum them up across all of the threads that are running. Okay, so let's take a look at this basically. You compare several schedulers, and if you look at Atlas, that's the scheduler, it performs much better than the best previous scheduler, as you can see over here. And its performance increases when bandwidth is much more precious. In this case, you have 20, this is actually not a realistic system, but you can always simulate to make sure your ideas actually make sense. So you basically have 24 cores essentially banging on a single memory controller. You're very bandwidth limited. As a result, system throughput is really low, right? But in that case, your memory scheduler becomes more important. As you see, there are huge differences in the system throughput of first come, first serve versus STFM. That's like multiple factors over here. And Atlas is about 17% better than STFM in this case. But the Atlas's performance improvements reduces as you go to the right. In the right system, it's also not a very realistic system in my opinion. You have 24 cores and 16 memory controllers. Bandwidth is very ample. And if the bandwidth is very ample, memory scheduler doesn't matter as much. Right? That's expected because you don't have much job to do scheduling, right? You don't have any requests queued up because you have a lot of bandwidth, a lot of memory controller, a lot of banks. But Atlas still buys you some performance, 3.5%. So the key insight is you have these light threads, and these light threads are being prioritized. As a result, you get much higher performance compared to previous schedulers. The downside, of course, is fairness. If you look at the fairness results in the paper, it's much worse. This is the worst. This is the scheduler that has one of the worst fairness. Maybe not as bad as FCFS, but it's definitely not as good as STFM or PAR-BS. Okay, so let's take a look at another result in the paper. I like these results because these are sweeping the space. So we're fixing the number of memory controllers in this case, and we're looking at number of cores. So we have 4 memory controllers, same applications, average results, and we're just comparing PAR-BS and Atlas in this case. If you look at this, as the number of cores increases, Atlas provides higher performance compared to PAR-BS. So this is good because this essentially shows that Atlas is making use of the limited memory bandwidth much better than a previous scheduler like PAR-BS does. Here the bandwidth is ample. You have 4 cores, 4 memory controllers. Here you have 4 cores, 32 cores, 4 memory controllers. So there's more analysis in the paper. I'm not going to go into that in detail, but I'd encourage you to take a look at this also. So clearly this scheduler is interesting. It's good at improving overall throughput, overall system performance. Basically, it's prioritizing compute-intensive threads. Really memory-intensive threads are not prioritized because they're attaining a lot of service. Of course, there's this interesting thing, right? If you deprioritize a thread because it's attained a lot of service in the previous interval, in the next interval, you're likely going to prioritize it a little bit, right? So there's a lot of movement that's happening in terms of the ranking between the threads that have some high amount of intensity. Unless you really have bandwidth that's ample, but that's not true in many cases. Okay, this is low complexity. Actually, this is the one of the simplest schedulers that we discussed that provides some sort of thread awareness. And actually, coordination among controllers happens infrequently. This is something that we haven't discussed that much, but for example, if you have parallelism-aware batch scheduling, you form a ranking of threads. And that ranking is formed when the batch is formed. Now, if you have multiple memory controllers, ideally you would like to have the same ranking across all of the controllers, because the same problem of memory level parallelism happens across memory controllers also between threads. But these controllers form the batches at different times, because their loads are not really the same, right? So the key question is, how do you ensure the same ranking across these different controllers? So you need to somehow coordinate them. You need to have a meta controller that actually forms a ranking. It increases your complexity a lot, and that ranking is enforced by all of the memory controllers. So that's not necessarily good. But in this case, you kind of sidestep the problem, because you look at this interval, and the interval happens to be large, and then you form the ranking across this interval. Basically, what happens is coordination happens infrequently. It happens across a very long number of cycles, let's say 100 million cycles or so. I think it was 10 million cycles over here, as opposed to every time a batch is formed. Okay, there are downsides to this also. Basically, fairness is a big downside. The threads that are ranked lowest or at the medium level, they get delayed significantly. So you get high unfairness in this case. The problem is not with compute-intensive threads, but the threads that are somehow in the middle. So I think of compute-intensive threads as mice, little rats. They're small. They don't actually generate a lot of noise. But these memory-intensive threads are elephants. They're very heavy. And what's happening right now is mice is being prioritized over elephants. That's good. Mice can run. But what is happening between the different elephants is problematic, right? You have some large elephants, you have even larger elephants, and they're really destroying each other's performance by being ranked. So if you actually have an elephant being ranked over a mice, the mice get squeezed, right? So you don't want that. We fixed that problem, but the problem now gets transformed between a fight between the elephants. And we're going to try to fix that problem next. Okay, so that's the paper, and you can take a look at it also. Any questions? I'm giving you a history that I find really fascinating. Okay, so this is actually the huge benefit of the scheduler. It's very easy to implement, and some of these concepts are inside the memory schedulers over here. But then we said, okay, we now figured out how to make performance work really well. How can we actually incorporate fairness into it? That's going to make our scheduler much more complex. So this is the realization, circa 2009 or so. Basically, you want to maximize system throughput, and you want to maximize fairness. We're going to change the definition of fairness a little bit over here. Basically, if you want to maximize, and this is data average across some number of workloads, as you see, 24 cores and 4 memory controllers. So I'm going to change the definition of fairness. Basically, we also realize that max divided by min fairness may not be the best approach, because usually you don't consider fairness in isolation from performance. So maybe a better definition of fairness is, and actually some other people have written papers based on this definition and showed that this is a good definition from a theoretical perspective, which I'm not going to get into. That's not our work, but I think there's some theoretical justice done to this metric also. So the definition is that figure out the thread that has the maximum slowdown in the system, and that is your definition of unfairness. And you want to minimize that maximum slowdown. I don't care about the thread with the minimum slowdown. I care about the maximum slowdown in the system. And if I reduce it, then I'm going to call that system more fair. And this is not a bad definition, actually, because you're trying to minimize the maximum impact that is on any thread in the system. You don't care about the max min. You basically try to lower the max. It has good properties because it does consider performance into account also, because if the min is doing well, why touch it, right? If it's not affecting the max, that's fine. That's the intuition behind this definition. Max divided by min tries to pull up the min, to increase the slowdown of the min, maybe unnecessarily. If the min is doing fine without impacting the max slowdown, that's okay. Just reduce the max slowdown. Okay, so that's the idea. That's why I think this is a better metric, and there's work that shows that this is probably a better metric theoretically as well. Of course, and this is weighted speed up. So ideally, you would like to be here, right? Your speed up is high and your slowdown is low. So let's take a look at other algorithms that we talked about so far. Atlas actually has a system throughput bias, as we discussed. It's over here, average across many workloads. ParBS has a fairness bias. It's over here. So none of these schedulers is optimal. Well, actually, both of these are optimal if you consider both metrics in some way, right? You really want to be somewhere here, but these are actually in the Pareto optimal curve if you're optimizing for both metrics. STFM is not good anymore, so it's somewhere behind. And FRF-CFS is actually much worse, as you can see. And first come, first serve is actually much worse somewhere over here. On these workloads, of course, this picture changes depending on the workload. Sometimes ParBS has both the best performance and best fairness if you look at a particular workload. But average across many workloads, you get a picture that looks like this, more or less. This picture is going to change later when I show you some other workloads also, some other system assumptions. But basically, none of these schedulers, none of the scheduling algorithms provides the best performance as well as fairness at the same time. So the key question is, how do you provide the best? And the realization is that if you have multiple metrics to optimize for and different applications, you need heterogeneity in the system. So this paper is the first to introduce a heterogeneous scheduling policy into the memory controller. It realizes that you have a throughput biased approach and a fairness biased approach. And if you want to maximize throughput, the fundamental thing to do is to prioritize the mice. Ignore the elephants. Form a ranking, and mice at different levels of granularity gets prioritized. The smallest mice gets prioritized over larger mice, and smaller elephants get prioritized over larger elephants. So you prioritize the less memory intensive threads. That's good for throughput because these threads have a lot more potential to keep their cores busy. But this leads to the starvation of the elephants. So it leads to a lot of unfairness, just like in Atlas. So if you want to take a fairness biased approach, this is one way of thinking about fairness. You take turns accessing memory. That's, let's say, round robin fairness. And that's another way of implementing these schedulers. Basically, if you do that, the elephant doesn't starve right now because other elephants don't get in the way. But now the mice is not prioritized. As a result, you get reduced throughput. So there is no single policy that is sufficient for all threads because threads have different requirements. So we want to achieve the best of both worlds. How do we do that? So we'll develop a heterogeneous scheduling policy. If you want high throughput, you would like to identify these mice and prioritize them. Prioritize these memory non-intensive threads. Now the realization is that prioritizing them is not bad for the elephants unless you have a million mice. But that's not the case in this case. The problem is that these elephants are killing each other. But if you prioritize one elephant consistently over another elephant, this poor elephant dies basically. It doesn't get service. Right? Okay, so basically unfairness is caused by memory intensive threads being prioritized over each other. So don't do that. Shuffle this thread ranking such that no elephant gets prioritized over another one for a really long time. That's the idea of shuffling. But it turns out actually these threads, these elephants have different vulnerabilities to interference. As a result, you need to be a little bit more careful in shuffling. So shuffle in an asymmetric manner. And what does this mean? Some elephants become the top elephant for a longer time than some other elephants because they are more vulnerable to interference. Right. I like this explanation. Okay, you can visualize it in your heads perhaps, right? Okay, so basically how does this work? I've actually given you the algorithm almost. I've given you two clusters over here, right? Basically, the memory scheduler groups the threads into two clusters. So you have some threads in the system. Basically, you identify what is mice and what is elephant. And non-intensive cluster consists of these memory non-intensive threads, and intensive cluster consists of memory intensive threads. All of the elephants are isolated here, hopefully. It's just the mice that are here. So you prioritize the non-intensive threads over the other ones. That's good for throughput. And within the colony of mice, if you will, you basically prioritize the smaller mice over the bigger mice. That's taking it to the next level. Of course, this doesn't matter as much as prioritizing this over this, but we do that anyway. Within the colony of elephants, now you actually need to have a fairness-oriented policy, which is shuffling the thread ranking. So let's take a look at how you do each of these. So for clustering, how do you do that? This is actually not an easy thing. Actually, there are really interesting questions here that is not explored in the paper. We form 2 clusters, for example. Why 2 clusters? Why not form 3 or 4 or 5? Clearly, complexity is one reason for not to form more than 2 clusters. But we did 2 clusters. So how do you do 2 clusters? We sort the threads based on misses per kilo instruction. Hopefully, these are the mice and these are the elephants. And we basically compute the total memory bandwidth usage, bytes per second, let's say. And you basically say non-intensive cluster consists of those threads that use a fraction of that total memory bandwidth usage. This is one way of doing it. It's not perfect, but it's not terrible also. So in this paper, the cluster threshold is about 10%. This alpha is less than 10%. And this is one of the problems with this sort of approaches, because this threshold is never easy to determine. Sometimes an elephant sneaks into the mice cluster. Sometimes a mice sneaks into the elephant cluster, which is actually a worse problem. An elephant sneaking into the mice cluster may not be that bad if you do the right thing in the mice cluster. But the other way around may be bad. Okay, so now we have 2 clusters. So what do you do between clusters? We already said that. You prioritize non-intensive clusters so that you can improve system throughput. And it doesn't degrade fairness, assuming you do the clustering right. Because non-intensive threads are light. So that's the downside of an elephant sneaking into the mice cluster. It may degrade fairness if you don't do the clustering right. Okay, so non-intensive cluster, as I said, you have a throughput-oriented scheduling policy. You prioritize the less intensive threads over others based on their MPKI. And that's the idea over here. You prioritize threads according to MPKI, you form a ranking, and you use that ranking. And this is the same mentality as we discussed before. Now, what do you do between these elephants becomes important, as we said. The idea is we want to periodically shuffle the priority of the threads in this intensive cluster, and we want to do this. So every thread gets to be the one that's most prioritized for some time, equal amount of time, let's say. This increases fairness, but treating all threads equally is not good enough if you want to really maximize your performance and fairness, because these threads have different priorities, not priorities, different characteristics. And because of these different characteristics, equal turns doesn't mean that you get the same slowdown. So let's take a look at an example. This is actually, we're going to go back to the fundamentals, random access and streaming thread. And we're going to have both of them access memory a lot. And we're going to look at answer the question, which ones slow down more easily? So let's take a look at this. So if both of them are extremely memory intensive, and if you prioritize a random access thread clearly doesn't slow down that much if you prioritize it. Its slowdown is 1, but streaming thread slows down by about 7x. Okay, you think this is bad, but if you do it the other way around, it's much worse. So basically, streaming thread, if you prioritize it over the random access thread slowdowns by 11x, with some assumptions, of course, in simulation. Now, this is happening because random access thread is actually much more vulnerable to interference compared to the streaming thread. Streaming thread is not very vulnerable, and we will see why. So let's take a look at these different threads. If you look at, well, these are rows clearly. If you look at a random access thread, because fundamentally it's random access, it has good bank level parallelism. The accesses are distributed across the banks because it's random access. That's the definition of random access almost, right? If the accesses were clustered in a bank, that was not really random, right? Okay, so they go to different rows also, and they get serviced in parallel if the thread was running alone. That's good. Okay, so all requests are parallel, you have high bank level parallelism. If you have a streaming thread, because it's streaming, by nature it looks like this. You basically have requests lined up to the same bank, to the same row, they get serviced, and then maybe you move to some other bank, right? Okay. Okay, this is a slow animation. It shouldn't be that slow. So all requests go to the same row, you get high row buffer locality. Now let's take a look at when what happens if you run these 2 threads together. If you prioritize a streaming thread, this is what it looks like. Random access thread gets slowed down a lot. Basically, it gets stuck behind the request of this streaming thread, just like we've seen earlier, right? There's nothing new here in a sense, except now we're thinking about the vulnerability of these different threads. So if you actually do the other way around, if you prioritize random access thread, random access thread slows down a lot. Basically, it gets stuck behind the request of this streaming thread, just like we've seen earlier, right? There's nothing new here in a sense, except now we're thinking about the vulnerability of these different threads. So if you actually do the other way around, if you prioritize random access thread, Streaming thread doesn't get slowed down that much because random access thread has only one request to this bank over here, right? So that's the idea over here. This thread, random access threads in general, are more vulnerable to interference. These are actually threads that cause interference, streaming threads. And we will see this later on also. Okay, so basically, this intensive cluster, we quantify the difference between the threads. We basically attribute some niceness to the threads. Niceness is high if a thread has high bank level parallelism. Niceness is low if a thread has high robuffer locality. And we have a metric to measure this. It's complicated. I don't recommend people to actually really go into the detail of it because it provides you very little performance on top of what you could do otherwise. But this is actually understanding the threads more. Maybe someone else can use this insight in a much simpler scheduler later on. I mean, this insight is clear, but how you actually incorporate it is not simple. So basically, you compute the niceness and you form the ranking in a niceness-aware manner, meaning that nice threads become the top threads more often than not so nice threads. Okay, so this operates based on quantum-based operations. So we basically have a previous quantum and the current quantum. In a quantum, you monitor the thread behavior, memory intensity, bank level parallelism, and robuffer locality. At the end of the quantum, or in the beginning of the next quantum, you perform the clustering, and you compute the niceness of intensive threads, and you form essentially these two different clusters as well as ranking. So ranking, of course, in the intensive cluster is not a fixed ranking. You shuffle the ranking very quickly such that no elephant destroys another elephant. So there's a shuffle interval where the ranking changes. So of course you don't want to recompute the ranking every interval. What you do is you can actually do an arithmetic change in the ranking. The paper discussed that a little bit. You can take a look at it. And in the end you get a scheduling algorithm that looks like this. The highest priority is the highest ranked thread. Requests from higher ranked threads are prioritized over others, which means that non-intensive cluster is prioritized over the intensive cluster. Within the non-intensive cluster, lower intensity threads have higher rank. Within the intensive cluster, you get rank shuffling. Everything else being equal, row hit requests are prioritized over others, and everything else being equal, older requests are prioritized over others. So incorporating this, once you know all of this, priority-based scheduling is easy. The difficulty is doing all of this over here. And the paper says it's relatively simple. It is true that the storage cost is relatively simple, but it's actually a complex scheduler to compute all of this. Okay, I'm not going to go through this in detail because we've already covered a lot of the previous work. I'm just going to show you results over here. But you can study this on your own. So basically, we wanted to achieve somewhere here. FRF-CFS gets us here, STFM is here, PowerBS is here, Atlas is here, similar to the previous graph. Where does TCM get us? It actually breaks that barrier, if you will. It becomes the optimal scheduler on these workloads. That's not true for all workloads, again. Basically, it's a heterogeneous scheduling policy that essentially breaks this Pareto front. And so you can take a look at the paper for more analysis. It's the highest performance as well as the highest fairness scheduler. So there's also a configuration parameter that you vary. This is also important. A configurable memory scheduler should behave nicely. And this paper shows that this TCM actually behaves nicely. So each scheduler has a configuration parameter. For example, STFM's configuration parameter is that unfairness, maximum tolerable unfairness, right? The alpha threshold. If you change that, you move like this. These are values that you get for different alpha values. That doesn't look good. FRF-CFS has also a parameter. It's actually called FRF-CFS cap. Basically, this is a parameter. How many requests can be reordered over the oldest request that you have? This is actually implemented in some AMD memory controllers. I don't know if I have it in this thing over here. Oh, I don't have it. It's in the STFM presentation probably. After we proposed this was proposed, this simple scheduler is proposed in our STFM paper, which I described earlier. It turns out this is something like this was implemented at the AMD controllers at the time. It's nice because it limits the number of reorderings that you can do over the oldest requests, but it doesn't solve the fairness or performance problem in a fundamental way. Basically, by changing the cap, you change the values in a way that looks like this, which is really weird. PowerBS has another marking cap. if you change the marking cap, you move like this. Basically, your performance doesn't change that much, maybe. It changes a little, but your fairness changes a lot. Atlas has this, I believe this is a quantum in interval length. Basically, it moves like this. If you look at TCM, the cluster threshold gives you a nice trade-off between fairness and throughput. So by adjusting the cluster threshold within reasonable values, you get a robust fairness and throughput trade-off. But of course, this is very much dependent on the applications also. So it's one of the downsides of TCM is it's brittle. Brittle in the sense that it has these parameters that are not easy to configure. Okay, so it's, even though they may not be easy to configure, it's a tunable knob, and it enables the operating system to trade off between fairness and throughput. We thought this would be a good knob for the operating system. And we could also enforce thread weights in the scheduler as well. Basically, OS assigns weights to threads. I like thinking about weights when I think about priorities. And TCM enforces thread weights within each cluster. And you can read the paper as to how it does that. Okay, I've already talked about TCM basically. So it's basically the scheduling policy that provides the best system throughput and fairness. But we're going to deconstruct that in a little bit because it's very complex to implement. It's very brittle in the end. But the key idea is you have a heterogeneous scheduling policy to cater for the needs of different schedulers. We're going to go back to a more homogeneous scheduling policy in a little bit. But this has actually benefits of its own, especially you really want to form two clusters if you have application level knowledge. So if you know that this application is latency sensitive, you can assign it to this cluster with better operating system level interfaces into the hardware. These don't exist at the moment, unfortunately. I believe they're going to exist within 10 years from now. Basically, if you have that knowledge, use it and prioritize those applications. This somewhat exists in the accelerators today, actually. I'm going to talk about schedulers for accelerators. We do it for accelerators, but we don't do it for cores today. In the accelerators, you know the deadlines of the accelerators, like a video encoding accelerator, or you know when you should finish a frame, or you know what kind of frames per second you want to satisfy. So you actually have a deadline in that case, and you can actually incorporate that deadline into the memory controller. In SoC memory controllers, those deadlines are incorporated, and we're going to take a look at that. So this is taking the general purpose memory controllers closer to the SoC memory controllers by identifying threads with different requirements. So I think there's a lot of merit into this still, but it's a little bit complex to implement. Okay, I've given you some upsides and downsides, I think. So let's take a look at the upsides. So this provides both high fairness and high performance at the same time. And its principles are actually applicable to higher level schedulers as well. If you actually blink a little bit, this looks like an operating system scheduler also. Operating systems usually identify threads as latency sensitive versus not so latency sensitive, right? Or they call it, some operating systems call them interactive threads. They're really latency sensitive threads from my perspective. And those latency sensitive threads are prioritized over other threads. So there are some similarities to the high level operating system schedulers. So this basically provides both high fairness and high performance. It caters to the needs of different types of threads, latency versus bandwidth sensitive. And it's relatively simple. Of course, we're going to construct that. You can never be simpler. But this is relatively simple compared to STFM, for example. Downsides, it actually has a scalability problem to large buffer sizes, which we're going to discuss. It actually has a robustness problem. This is what I called by this being brittle. Clustering and shuffling algorithms are actually relatively brittle. And ranking is actually still too complex. We're going to talk about that in a little bit. Actually, that's the next thing that we're going to talk about, and then we're going to be done for the day, I think. Any questions? Sounds good? Okay, so this paper definitely pushed the boundary. Now let me, in the remaining time, hopefully less than the remaining time, I'll deconstruct a lot of the things that I said. This doesn't mean that the scheduler doesn't have its merits, but you always want to be less complex. And let me give you the idea of that deconstruction, if you will. Basically, the previous scheduler is complex, right? It's good maybe, but it's complex and not robust. Ideally, you want to have a mechanism that's simple and robust. I'm not going to promise easy to reason about. None of this is really easy to reason about because there's so much interaction going on between different threads with different characteristics. And the memory scheduler is already a complex thing, right? It's not so easy to reason about. But whatever I said earlier will hopefully exercise your thinking. Okay, so basically, all of the previous schedulers that I just described have, what they do at a high level is they monitor application behavior and they rank threads. STFM doesn't exactly work this way, but others actually form a ranking of the threads. So, and then they enforce the ranks. So enforcing the ranks actually is not easy, so you need to do this sort of search. You can simplify it, but memory scheduler becomes more complex. Computing the rank is actually complex also. So if you do full ranking of the threads, actually this increases the critical path latency, scheduler area. It does improve performance and fairness. So the key question is, can we get the performance and fairness improvements without having this full ranking? Let's take a look at, so we're going to add another metric into the equation. Not just performance, fairness, but also simplicity. And things are going to get more complex going into the future, like if you add energy, how does that go into memory scheduling? So let's take a look at these three different axes. Ideally, you would like to maximize them. And a good scheduler actually maximizes them. FRF-CFS is somewhere in between, assuming some scale for these axes. And that's application unaware. It's very simple, but low performance and fairness. If you look at PARBS, Atlas, and TCM, they're application aware, and they put you in interesting places over here. So basically, they're application aware. They give you higher complexity, but they also give you higher fairness, not always, and higher performance, clearly. So the key question is it essential to give up simplicity to optimize for performance and or fairness? And we would like to achieve all three goals, and it turns out the simple schedule that I'm going to describe, it's actually this red one over here, that gets close to all three goals. Again, this is workload dependent, but across a large number of workloads, this works nicely. So the first observation is full ranking is not great. It's sufficient to separate the application into two groups rather than to do full ranking. So you monitor, as opposed to doing full ranking, you basically form two groups, vulnerable to interference and interference causing. And you somehow prioritize the vulnerable to interference threads over the other ones. So this gives you low complexity compared to full ranking, clearly. This also leads to lower slowdowns than full ranking, because full ranking actually has the problem that you're really too strict. Basically, why do you need a full ranking across all of these threads? If this thread, why do you care about thread 4 being ranked over thread 3 if they're not really interfering that much with each other, right? That's the key realization over here. You don't want full ranking because it's too rigid. It unnecessarily prioritizes one elephant over another elephant. And if you somehow group things at a coarser granularity, you become a little bit more flexible. Maybe some of these elephants are very vulnerable and some of these other elephants are not so vulnerable. And this behavior actually changes dynamically, potentially very quickly. So ranking is too rigid. As a result, it leads to higher slowdowns and maybe performance issues, but it's also harder to change very quickly. So you really want a mechanism that's not too rigid, coarser grained, and also easier to change. Easier to change I didn't give you, but if you become coarser grained, you're less rigid in general. So that's the idea over here. So then the next question is, how do you classify the application into two groups, vulnerable and interference causing? You can actually use many of the complex mechanisms that we described, but we're not going to do that. Our goal is simplicity over here as much as possible. And what is a simple metric that tells you an application is going to be interference causing very quickly? And the idea is very simple here. If you serve a large number of consecutive requests from an application in a given time interval, this causes interference. And if you realize that, this is actually very similar to least attained service at a much finer grained interval. Right? Basically, if an application has attained service, a lot of service very quickly from the memory scheduler, it's likely that it's going to cause interference soon. At least the trend is like that. So blacklist it for a while, meaning deprioritize it for a while. Basically, the idea is you group applications with a large number of consecutive requests as interference causing, you blacklist them. And you deprioritize those blacklisted applications. You clear the blacklist very quickly to give the application another chance. Very quickly means there's another threshold, which is always ugly. So there's a threshold in this paper, which is the blacklisting interval. I think it's about, I don't know, 5,000 cycles or so. But that enables other applications to be prioritized. So it's actually a very fast-moving, very quick decision-making system, much faster than the ranking-based system. As a result, it adapts much more quickly. Okay, clear the blacklist periodically, basically. So it's lower complexity and finer grained grouping decisions. As a result, you get lower unfairness, also higher performance. Some of this is also not easy to explain as well, right? We don't do ranking, so one of the big benefits of ranking was parallelism awareness, so we got rid of it. And I never liked that part of this scheduler because you're not parallelism aware anymore. But maybe there is some other mechanism to incorporate that over here. But it turns out this actually is close to the best in all of the metrics. It's the best in terms of performance. Somehow it happens to be that way. It's not the best in terms of fairness. And it's not the best in terms of simplicity, but it's up there. So, as you can see over here. Okay, so let's take a look at these different axes a little bit. So you have performance, unfairness, max slowdown, lower is better, performance higher is better. Ideally you're here. And it turns out the different schedulers end up being here for different applications, as you see over here. So blacklisting is this black one over here. It's not Pareto optimal, but it's close over there. As you can see, TCM doesn't work well for all applications, so it's different from what I've shown you earlier. Because it's not very robust, basically. You need to really tune the parameters for the workloads that you have at hand, and you really don't want to do that. You want to minimize the parameter tuning that you need to do for any hardware component in general. And TCM has a lot of these moving parts, meaning components that you need to tune. Okay, we already said that. So complexity, this is actually really interesting. It's in the paper. These are schedulers that are designed at some level of optimization based on the RTL code. And we figured out the critical path latency and the scheduler area with some, I think it's 65 nanometer library over here. So ideally you would like to be here clearly. And FRCFS is actually close to there. FRCFS cap is pretty much on top of it. PowerBS is far away, as you can see. Atlas is actually over here. I think it can be optimized more. I'm not really sure why is it there. And TCM is actually somewhere in between, and blacklisting gets you much closer to here. It's not the simplest scheduler, but it's close to the simplest. Okay, so now we've achieved lower complexity also while achieving almost well, it's the highest performance according to these results, but you don't know what workload will exercise things differently. But you achieve very good performance, very good fairness, and very good complexity at the same time. So it's a good trade-off between these different metrics. Okay, any questions? And this is the longer version of this paper. It's called BLISS. So we've achieved bliss in memory scheduling like that. That's not absolutely true. There's more to do in this area for sure, as we will see later. Okay, any questions? So not tomorrow, but next week we will pick up with even more interesting cases where you have heterogeneity in the system, like a CPU, GPU, and hardware accelerator. Then how do you do the memory scheduling? And then we're going to talk about, and actually these systems have to do that sort of memory scheduling. They have many, many accelerators, GPUs, CPUs, and who knows what else inside there. As a result, the schedulers that we're going to discuss are going to be applicable to these systems. And then we're going to continue the memory interference and quality of service. Any questions before we part? Okay, I guess have a good weekend. I'll see you next week.